就我係探會嘅職員啦。今日歡迎大家嚟到出席呢個今日嘅講座。由拉斯坎帕納斯，辛苦嗰啲嘅中文天文台嘅科學家由你別列茨基先生 Mr. Yuri Beletsky 主講嘅講題阿塔卡馬沙漠上嘅專業同埋業餘天文嘅觀測。今日講咗咧係由太空館同埋香港天文論壇合辦嘅，並由謝瑞麟基金會咧就向呢個天文論壇咧贊助。Good afternoon, my name is Eddie, Assistant Curator of the Hong Kong Space Museum. Welcome all of you to join this lecture today. Today's topic is professional and amateur astronomical observation above the Atacama Desert, presented by Mr. Yuri Beletsky, scientist of Las Campanas Observatory. Today's lectures is jointly organized by the Hong Kong Space Museum and Hong Kong Astro Forum, with TSL Foundation as the program sponsor for the Hong Kong Astro Forum. 天文論壇咧就主要咧就為咗就俾太空館即係香港嘅太空館嘅和鏡班嘅同學咧就互相通訊啦，同埋咧分享和鏡班嘅心得咁開放。咁同時咧就都為咗咧就可以任何天文同好有個交流聚腳點嘅。咁咧就I also speak in English. Hong Kong Astro Forum is openly mainly for the participants of the telescope making course of the Hong Kong Space Museum to communicate with one another and share their experience in telescope making. At the same time, it also provides a platform for all astronomy lovers to exchange their experience. 咁最後講多兩段。咁咧就大家可能會聽到，咦？有謝瑞麟基金會做咩咧？就係、大家知係一個慈善信託。咁致力咧就推廣華人社會中嘅藝術創作啦、保育同埋傳承嘅工作。咁佢亦都支持呢個有關嘅佢自己嘅傳統嘅珠寶手作嘅工藝、粵曲嘅粵語流行曲保育同埋推廣咧，最緊要咧同我哋太空有關嘅，包括天文啦咁樣。The TSL's foundation is charitable trust in Hong Kong and is committed to foster the works on creative arts, preservation, and inheritance in the Chinese society. Currently supported projects include the inheritance of traditional jewelry, craftsmanship, the celebration of Cantonese popular music. Of course, foster the Astro Photography from night sky observation. 咁咧就唔講咁多啦。咁咧就Yuri 大家都知啦，佢咧就嚟自南美嘅一個天文台啦。咁咧今日我哋講座咧有兩節嘅，第一個講佢專業天文學家嗰個即係好多嘢發生㗎，有好多嘢。今日我哋睇下佢希望大家能夠可以知道一啲最專業嘅而家嘅前做緊乜嘢。咁咧就佢嚟得喺度咧，都多謝謝瑞基金嘅贊助啦咁樣。咁我梗係唔會講似咁嘅嘢啦，係嘛 ？hold 咗咁講一講，佢哋都本身係一個好出色嘅業餘天文學家。咁咧就當然佢哋同我哋分享咧就係、第二節係講佢業餘天文嗰個事業。咁張相係自己㗎啦。咁大家入嚟嗰時，見咗個入嚟嗰個喺個張台都有佢自己Yuri 嘅作品嘅。And I'd like to also introduce, of course, Yuri is also a professional astronomer. And according to Robert, our curator standard, he's an expert in all the planetary science, something, and related to the planetary science. And also, of course, it's also a brilliant amateur photographers. 咁咧就以往下嘅今日嘅講座咧就會全部用英文嘅。咁就開頭講啲講就係為咗啲大家知道。貪我哋係雙語嘅，咁但係咧，我哋為咗一個講座嘅流程起見咧，就會後邊咧就全部用即係英文嚟講啦。咁咧就喺開始之前咧，我都請我哋嘅館長Robert 咧就致送一啲嘅紀念品俾Yuri. Before the lecture, I would like to ask our curator, Mr. Robert Lam, to present us a souvenir to Yuri for our appreciation. Awesome.
Hello, can you hear me well?
Yes.
Okay. More time. But this is the only thing I know in companies. I'm sorry, so it's going to be in English. That's the only thing. Anyway, again, my name is Yuri Beletsky. I'm a professional astronomer from Carnegie Las Campanas Observatory. Our Carnegie Institution for Science located is in the United States, in Pasadena, in the Washington, D.C. But the observatory itself, where the telescopes are, is located in Chile. So I will be telling you about astronomy in Chile. So how we do astronomy, what kind of discoveries we made in the past years, and to give you a little bit of insight about astronomy, professional astronomy, how we do things. Because many people, when they see just the pretty pictures, you don't really see probably all this processes going behind. So you'll see what it takes for us to take these absolutely amazing results sometimes and to show this to the public. A little bit of a word about the observatory itself. Here on this map, you will see where astronomers put their telescopes. And here in my talk, I'll be focusing mainly on the ground-based astronomy, So I'll be talking about the telescopes located on the surface of our planet. So I'm not going to be talking about the space telescopes, which are floating in space. It's a completely different thing. It's more like a space science. But we'll be talking about telescopes located on the planet. So, and from this plot, you basically see where the telescopes are. So there are a few places in the world, so not all planets are suitable for astronomy. So there are very specific places where astronomers go and install the telescopes, and we will see later why we go to very specific places, and we cannot simply put a telescope, let's say, here in Hong Kong, and try to do some astronomy. So it's a bit more complicated. So as you see, immediately the places where astronomy is happening on the ground is mainly like southwestern part of the United States. It's Argentina, Chile in the southern hemisphere, in South Africa, Australia, even in China. There are really nice regions close to Beijing and the western part of China and in Tibet where the conditions are suitable for astronomy, plus a couple of places on the islands like Canary Islands and Hawaii, United States. Here's the list of the largest telescopes on the planet, the ground-based telescopes. It's a list of 18 telescopes with a diameter of primary mirror starting from 6 meter up. It's from 6 meter up to 10 meter telescopes. And out of the 18 telescopes here in the list, 7 biggest largest telescopes are located in Chile. So Chile has become over the years what we call astronomical capital of the world. Because the biggest telescopes are coming to Chile, and we will see later even bigger telescopes are coming to Chile as well. So which makes this country is pretty small, but the question is why Chile? And I will try to describe in my presentation why so many astronomers looking into Chile and selecting Chile is the future space for future telescopes as well. As I said, Chile has become a really amazing center, like a laboratory for astronomy to study various processes in the universe, starting from the formation of stars, evolution of solar systems, everything you can imagine about studying the space. So it's done now from Chile to the unprecedented scale. I'll try briefly to describe the major discoveries made from Chile. Of course, it's impossible to talk about everything because the list is really, really long. I'll just try to stop on very few points, which are important here, I think, such as the discovery of extrasolar planets and their atmospheres, as well as the first image of an exoplanet ever detected from the Earth. Also, they come into the understanding of the physics of supermassive black holes and a black hole in the center of our galaxy, as well as the study of the supernovae and the accelerated expansion of the universe, which was this study was awarded the Nobel Prize recently, as you know. The physics of gamma ray burst and the satellites of our galaxies in the Milky Way, and more and more and more. So there's so many things to talk about. We'll just try to cover just a little bit to give you a feeling what we are studying, and then I will switch to main topic of the presentation as the life astronomers. So the first exoplanet was discovered in the detection direct imaging of the planet was done in April 2004 at ESO, European Southern Observatory, on the VLT, Very Large Telescope. This image has become extremely famous. What you see here is the host star, which is in blue, and this tiny object in the lower left, which is a planet. That was proof that this is the first image of a planet itself. We've never seen it before. So we have to be, you have to understand here that this is like a false color picture. This is the color is not real. It's like artificial color, which just gives you an idea about the temperature. So the blue the color corresponds to the hot temperature, while the red color corresponds to the lower temperature. But essentially, this is the presentation in the infrared. It was the first image of the planet. And then there was a huge news, of course, everywhere, because until this moment, we knew about the existence of planets. For example, which were detected using different methods, like Doppler spectroscopy, when we indirectly can say, oh, this planet, this star has a planet. But we could see it only from the spectroscopic study, and it was not direct. Here, this is the image of the planet itself. So now we can, it was the proof that planets kind of exist and we can see them. Another interesting study, has been going for years, we were trying to understand the physics of our own galaxy. As you know, we live in a spiral galaxy. We have like a vortex of stars rotating around the center of the galaxy. But the question was, what is located in the center? What is there inside our galaxy? Because the physics was not really well known. We knew there was some kind of massive objects should be in the center, because from the study of the rotation of stars around the center, we knew that all stars rotated around the center. But we really puzzled what is exactly in the center, and also astronomers didn't know the mass of the objects which are located in the center. So there was a group of German astronomers which were using the VLT, a very large telescope of European Southern Observatory, in the infrared. We are looking at this is the area of the galactic center. The galactic center is somewhere close to the center of the image. We still do not see the center of the galaxy because it's completely hidden from us with a huge layer of dust. So even in the infrared image, so we can't really see the galactic center itself. But we can precisely pinpoint the area which is called the galactic center, the area of rotation. And why infrared? So what astronomers do, how we study the universe, we are looking not on the visual band, or like a visual vision. We always trying to explore different wavelengths, ranges, and in this case, the explanation of infrared, why we're doing infrared. If you see on this plot, it's the same image of the object on the upper left. It's the number that refers to the wavelengths of the filter which was used in this case. In the upper left corner, this is the blue filter, so which means we are looking in the blue band, then we are going to the visual, and here this is like, for example, our eye would see on the sky, we are sensitive enough. Then we move into red, and then starting from here, we are moving to near infrared and up to the K band, which is 2 micron. So what you see immediately, if you look at the sky in the visual band, just looking like with our eyes, you will see just a cloud. And then actually this is a molecular cloud, it's called molecular cloud. It's a cloud which is full of hydrogen and dust. And for visual observations, you will see just a black patch of the sky. There's nothing there. But once we go into the infrared, you will see the stars. So those stars, they not just appear because they just suddenly got brighter. No, it's because in infrared we can penetrate through the dust and we can see through the dust. So this is the specific of the infrared astronomy. So when we go to the far infrared, in this case like going to 2.16 micron, we start to see through the dust. And this is again, it's a technology which was used a long time ago by the militaries, for instance. So this is why infrared technology was so difficult to get into astronomy, because the first application of infrared was actually military, because in military, the infrared, like in K-band and H-band here, they're used for the missile guiding system, because when you shoot a missile, it goes through the dust and look for the target. So this is exactly the application which military were using. So astronomers starting from the 70s, they slowly start to get their hands on the technology, and now we can use this technology like for peaceful purposes to study the conditions in the universe. So this is how we got to see the area which is really close to the galactic center. Now, what what we did, once we looked into the area, and what astronomers did, they spent about 16 years looking constantly on exactly in the same area around the galactic center. And when they discovered over the 16 years, they were recording positions of the stars which were moving around this is the galactic center, which were moving around the galactic center. So then when they got 16 years of such observations, they could trace the orbit of each star which attended the galactic center. And this is how they managed to precisely measure the mass of this object located in the center of our galaxy. So, and it turned out that the mass, it turned out to be a so-called supermassive black hole with a mass of about 4 million solar masses. This is huge object. So all stars now, we know it's a black hole. All stars are in this supermassive object, and we know now the mass, which is kind of fundamental parameter to in understanding of the evolution of our galaxy as well. So what you will see here, this is a kind of movie I'll try to start with. So what I'm going to show you, this is the result of simulation by the German astronomers who studied for 16 years this area of the sky, and you will see when I click now, you will see the movie. This is the result of the 16 years of study. For some reason it doesn't play. It says doesn't work? Okay. Oh, I'm sorry. Anyway, I don't see, it's really strange for it. Sorry. So the idea was that we will see all those colorful stars start to move around some invisible object which is like here more or less. So, and looking at the movement of all those stars, you can, first of all, you can pinpoint the object precisely, and secondly, you can precisely measure the mass of this object. So this is what has been done. So it's kind of time lapse, what we call now the time lapse, of movement of all the stars around the center of the galaxy. So that's the idea behind this movie. And how it was done, I can show you the obstacles when we astronomers trying to obtain some data, and some people complain like now everybody has this digital camera, cell phones, and you say, oh, sometimes my phone is not good, you know, the camera is not good, there are lots of bad pixels and so on. I'll give you just one glimpse of what you expect from the professional astronomer. So what you see on the left, this is like a single image coming from the astronomical camera, okay? So it's horrible. What you see here, the white stripes, it's all defects. It's like a bad pixels, you know. On the right side, this is the result of the post-processing using sophisticated techniques, combining all the data, properly calibrating the data, and this is the final result. So this is what astronomers do. So from the image on the left, we're getting something like this. It's much better. So it's extremely complicated technique, and sometimes it works for us. So don't complain about the cell phone. So now the other thing which we are doing in fundamental study, we are studying the supernovae and trying to understand the accelerated expansion in the universe. So here you see the image of the cluster of the galaxies taken with extremely long exposure time. So most of objects here are actually not stars but the galaxies. So what happened is the work was done mainly in the Atacama Desert, which is also located in Chile. And astronomers were using so-called supernovae, the stars which explode at the end of their life cycle, to map the distance. There are several classes of supernovae which is called supernova type 1a, which has a property which is similar to each other, which means the amount of energy released in the explosion of supernova 1a stars, it's constant. So now we know the exact amount of energy which is released by the star, and using this parameter we can map now the distance to those supernovae. Since those supernovae happens in different galaxies at different distances, we can basically now just map all those distances up to really long, distances as far as we can see those objects. And it turned out that in those years when the study just began, we didn't really know exactly what's happening to our universe. There were several ideas whether our universe is expanding or contracting, or it will just expand until a certain limit and then will contract again. So there were lots of theories, but there was no observational confirmation. So the supernova actually was the tool to show to astronomers that our universe is expanding, and it's not just expanding, it's accelerating. So it was a fundamental discovery which was awarded the Nobel Prize. It will help us understand enormously the fate of the universe, so what's going to happen to us. And to constrain the age of the universe as well. And also, it brought the idea of the theory about so-called dark energy, because there was something in the universe which we couldn't really understand what's happening, because in order to expand and increase weight, you need something, source of energy, which just gives it to the expansion. But all existent, like a bionic material, was not enough to explain this fate. So this was the first hint. There is something in the universe which we don't know what it is. Astronomers and physicists now use the term dark energy, but use dark energy doesn't mean it's dark. It's just something which was like a fancy name. There is some kind of energy which should exist according to current theories, which gives this acceleration rate to our universe to expand. So that was one of the other fundamental results obtained at Chile telescopes in Chile. And here what you see is basically the objects which help a lot to explain this theory is, as I mentioned, the supernova 1A. So essentially the physics is it's exploding star. There is a binary system, a dwarf and giant, or the main sequence star. So there is a material which is going from one star to another, and at some point the small star gets too much mass, too much weight, it just cannot sustain the accretion rate anymore, and it just explodes at an enormous rate. So this is called supernova 1A. Now, sorry for this, something happened here. So the ground-based astronomy, unfortunately, we are limited by lots of factors. So it's not easy. For example, when you go in space, when you put the telescopes outside the atmosphere, so you basically, the telescope is floating in free space. There is no light pollution. There is no clouds, nothing which prevents you from getting very sharp images. But once the telescopes are on the ground, there are parameters like atmospheric turbulence, which actually blurs the images, so they become less sharp, and they do not allow you to see objects crystal clear. The weather changes all the time. Even at the Atacama Desert, the weather is not perfect. Sometimes clouds come, clouds go, and it affects your observations, of course. Other parameters like content of water vapor or carbon dioxide in the atmosphere changes the transmission at certain spectral windows, so we can't really see the objects in the light we want to see. And also aerosols and artificial light pollution also limit our capabilities of detecting extremely faint objects. So in this case, of course, astronomers, we are challenged, so this is why we are always trying to find places which are better. Using those parameters, of course, we're trying to go as far as possible from the big cities. We're trying to go as high as possible to high mountains. And the places should be as isolated as possible from the all artificial activities like mining or stuff like that. So on this image you see it's a representation of light pollution map on our planet, and you see light pollution pretty much defines our continent pretty well, especially like in Asia, Europe, and United States. I mean, almost you can see total continent glowing now. And it's becoming a serious problem for astronomers, because even though you saw previously you can find places where you want to go to the telescope, but you simply cannot because there's too much light. If you look like here in Asia, you see here in Japan, like Europe, United States, it's becoming increasingly difficult to do professional astronomy in those places because of the increased light pollution. And here is just one example of predictions. This map was created about 10 years ago. So it's a map of Europe. On the left side is the situation of the 1998. which you can see, Europe is still mostly was like a green zone. So green zone, which means that you still can see Milky Way, but pretty poorly. Now by 2025, red zone means like you basically don't see any Milky Way. It's kind of like it's Hong Kong. So now imagine by 2025, most of Europe become like a big Hong Kong. Well, in terms of population too, I think. So, but it's absolutely a disaster for astronomy. Most of the observatories in Europe now, they become more like a historical places because they're like traditionally, as you can imagine, when astronomers were building the observatories, they were building them close, of course, close to the city, a little bit outside of the city, but nobody was thinking like in 50 years, the amount of population will explode by a factor of 10. So suddenly, the observatories just became, like a museum under the open sky, because the light pollution was so strong that it was very difficult to do astronomy, and in many cases it was really impossible to do astronomy. So this is why astronomers in the middle of 2000 started to get this idea to move the telescope as far away as possible. First of all, they were looking at Europe. They went to the Alps mountains. They went in Spain to Sierra Mountains, but then it was still not enough because the growth of the cities, the rate was so high that astronomers wanted to go beyond that. So they were looking for different locations, and South America, South Africa, and Australia became much more favorite candidates as a new place for astronomy. Now, when we look for the places, there are some essential parameters which should be taken into account. So when we look for exact place, have to make clear that the number of clear nights is sufficiently high, so which means about 300 nights a year and even more. The sky should be dark. That's this. Astronomical seeing in this case it defines the image quality. So how good the image quality is, or another way to describe this is how stable is the atmosphere. So the more stable the atmosphere, the better the image quality you're getting in the telescope. Sky transparency. What is sky transparency? Like in Hong Kong, you see the pollution is pretty high. You get lots of aerosols coming from your cars, and you see sometimes when the light pollution is too bad, the setting sky, the setting sun, and gets absolutely red. And this is the aerosols which are in the atmosphere. So now you see if the sun is red, so extinction of the light in the atmosphere is so high that it basically prevents you from observing extremely faint objects. So this is why we need to escape the city. Well, weather conditions, obviously, we should be away from the typhoons, from cloudy conditions. Infrastructure at the same time. When you build a telescope, the observatory somewhere, you have to make sure that it's becoming still accessible in terms of roads, in terms of electricity, internet. So you still have to get to the site. You cannot build a telescope in the middle of nowhere, for example, to put somewhere in Antarctica and expect to go there like every week. So it will be very difficult. So that's why it's one of the important moments. The legal and environmental restrictions. It's very funny, but actually astronomy, you can think it's about investment, long-term investment. So the cost of professional observatory is tens of millions of dollars. So you can't really put tens of millions of dollars somewhere, and then like in 5 years there will be another political change in the country, and everything can just disappear completely. So you have to find a country with a politically stable situation, and also the cost. You should try, of course, to cut down the cost as much as possible. Well, astronomy is very expensive science, because telescopes cost a lot of money, and scientists then should be there. So there are many parameters here in the list. Now I'm just going to repeat the list where the big observatories have been already built, and I will focus now on Chile, trying to explain why Chile and why most astronomers now select Chile as the place for professional astronomy. So here, there's a slide which shows you essential distribution of all existing large telescopes by diameter. So diameter of each circle represents roughly the size of the primary binaural telescope. So when we are talking about big telescopes, all big telescopes these days are into the camera. Now, why astronomers go bigger? So the bigger the telescope, the bigger the area which collects the light. So the more faint objects we can observe with the big telescopes. The bigger the telescopes, the fainter the objects we can see, and at a reasonable amount of time. So on the left side, these are existing telescopes. On here, those two, it's those 1, 2, 3. These are planned ones. I will talk about them a bit later. But you see, the size of the telescopes ranges from like a 1 meter up to like a Keck telescope to 10 meters. This is the range where we are. So for all these telescopes, the place should be perfect. And the first problem which astronomers encounter in ground-based astronomy, as I mentioned before, the atmosphere blurs the images. So unfortunately, in the atmosphere, in the upper atmosphere, at the level of about 10 kilometers and a bit higher, there are jet streams. There are lots of turbulence, which basically acts like, in a way, like a lens, floating lenses, which are blurring the image. And on the left side, this is an image of the galaxy taken from space. And here, this is exactly the same galaxy taken from the ground. And you see, the problem here is not, the telescope is perfect, it delivers amazing quality. The difference is the atmosphere, which completely blurs the image, and unfortunately from the ground, we cannot get the same resolutions we get in space. There's a huge advantage of the space astronomy that we are getting. Telescope works on the theoretical performance, while on the ground, unfortunately, we get lots of problems with the atmosphere. So this is why we always have to find a place where the influence of the atmosphere is minimal. So typically it happens in the mountains. So the higher we go, the better the image quality. And here's a representation how astronomers are actually looking for those places. So in order to find a good place, it's not just enough to look for the map and just, like in this case, we plot the average cloud coverage map across the whole planet. And the darker color means places with the least amount of clouds. So what we can see immediately from this guy, it's like a first assumption when astronomers start to look for a place for observatory, to see which place has the least amount of clouds. Okay. So we immediately see that West Africa is Atacama Desert in Chile, southwest of US, then places in Africa, a little bit between the Western China and the border with Mongolia, and Antarctica, surprisingly, in Australia. So this is actually kind of super useful information because it narrows down the search area, trying to understand where potentially we can go from here. Then astronomers will start to add more parameters to the cloud map. We start to add the parameters, like the first parameter is altitude. So we want to go as high as possible in order to eliminate the influence of the aerosols and to get more transparency. Parameter number 2, we are also adding the content on the water vapor. So the less water vapor in the atmosphere, the better it is for the infrared and especially for the submarine astronomy. So typically this parameter correlates with the altitude. So the higher we go in the mountains, the less water vapor. So this is the reason why astronomers were building observatories as high as possible. So we are trying to get as less as possible of the water vapor in the atmosphere. And of course we here combine with the parameter from before, it's the total cloud cover. So once we combine everything, so we build like a weighted map of potential locations where we can go. And you see the first one now, the green color shows you the best possible places. And here it's fine, strangely enough, it's Greenland. You see here in Chile, in the US, and in Tibet in China, it's one of the best places. And those is the Hawaii, and here will be the Canadian islands. So you see, the map is getting denser, sparsely, so you don't really, you see there are very few places on the planet where we actually can go and build something. And Chile, this is the typical Chile view from Chile, from space, and most of the area which you see here, this is the Atacama Desert, this area here, and the Andes Mountain on the other side is Argentina. So Chile is pretty interesting country. It's very narrow. It's like a few 4,000 kilometers from north to the south. On the eastern side is the Pacific Ocean. On the western side, on the eastern side, the Andes Mountains. And Atacama Desert just in between. The country is extremely narrow. The widest part of Chile is about a couple of 100 kilometers only, but it's very long. Now, Atacama, when scientists started to explore it in more details, they found out that first of all, the desert is extremely long. It's about 1,600 kilometers here. And now, amount of clear nights in this region of the planet is amazing. It's like enormous. It's about more than 300 nights. The place is very dry. There is no light pollution in most of the places in Atacama Desert. And there's an excellent atmospheric transparency. So there's low in aerosols and other types of dust in the atmosphere, which helps a lot for astronomy. And here, I'll just zoom in a little bit to show in more details where the desert is located. So this is Chile, as I said, it's about 4,000 kilometers from the north to the south, from Chile and Patagonia up to Peru and Bolivia here, Argentina on this side. But only like 25% of the country, which is called like Atacama Desert. It occupies north of Chile, from Peru down to the region which is called La Serena here. And the question is, scientists were trying to understand why it happened that this part of the tiny portion of the coast of Chile became so good for astronomy. What makes this place so special? What makes it so special? There are a few factors here. So the first one is the wind pattern, which in this south of the country, the wind comes mostly predominantly from the Pacific Ocean, while in the northeast it comes from the mountains. Here the mountains are really high. They're about 4,000 to 6,000 meters. So they're blocking the wind coming from this is Brazil. The Amazonian River is just right here. There's lots of moisture coming from the east. But the mountains are so high that most time of the year they just block this moisture coming from the east, while the ocean itself here is very cold. It's there is so-called famous the Humboldt current. The current, very cold current coming from Antarctica, and goes up along the coast of Chile, and the temperature of this current is so low that it keeps the inversion layer, so the water does not evaporate at high rate. So it keeps the inversion layer so low that it becomes even lower than the coastal line of Chile here. The coastal line is like a plateau at the elevation of a few thousand meters. So what does it mean that the inversion layer becomes so low? So it means that the clouds never goes up. So we're getting in the situation when from the east, the region is closed completely by extremely high mountains from 4,000 to 6,000 meters. And on the other hand, there is an inversion layer which always stays below the surface. So there is an area intrinsically now which becomes free of clouds. There are no clouds. It's extremely dry because there's no humidity coming, and it's completely cloudless most time of the year. And this is the typical view from the satellite. Okay. Sorry, I missed the change the microphone. So this is the typical image, satellite image of the South America. You can see Chile. And look at the region here. It's absolutely cloudless, and there are no clouds. And the red spot shows the place where my observatory is. So we are located in the southern tip of Atacama Desert, while most observatories are located from this point up to right here. So this is the region where all big professional observatories are. And you see it's absolutely amazing. So it's, there are clouds always over the ocean, and they always stays below the level of about 500 meters. And also you see all the more clouds like more resides on the other side of Andes in Argentina. They never really goes through the mountain because the mountains are too high. So the ideal conditions are just right, this tiny stripe along the coast of Chile. Now, to put in perspective how far Chile from you, just we're here, and this is here. Typical travel time from Hong Kong would be about 30 hours. And the funny thing is, we are actually almost on the opposite side of the planet. So it doesn't actually matter whether you fly through Europe or through the United States. It's almost the same. It's 11 hours time difference. So Actually, it's not bad because, like for us, for astronomers, when we observe in Chile, we are on the night schedule. When we come to Hong Kong, we are fine. We don't have a jet lag because it's daytime here. It's pretty convenient. I just feel like I don't have a jet lag anymore. it's really nice. But the problem is, it's really far. So if you want to visit Chile, it's pretty long flight. So it's pretty much you have to change it somewhere. But trust me, it's worth it. Chile is a beautiful country. You have a chance. I would suggest you to do it once. And when you go to Chile, this is the first picture what you will see crossing the Andes. In this case, this is Andes Mountain, the beginning of Atacama Desert. It's absolutely surreal picture. I mean, this is picture from the cell phone. There's nothing like no Photoshop here, no color correction involved. It's just a snapshot how you see absolutely blue sky, almost no clouds, and surreal foreground, like different colors of the mountains and the sand. So this is your first view on Atacama Desert from the plane. And this is how it looks in real. So when you get on the plane, just take a bus. It's absolute desert. If I, for example, put here a title instead of Atacama Desert, I was put like a Mars, you would totally believe me because I mean it does look like Mars. And actually, it's not a joke because NASA and the European Space Agency they did tests for their Mars rovers. Their space vehicles were doing tests in Atacama Desert because the conditions are so similar to conditions which you can find on Mars that it was a really good testing spot for this kind of technologies. Here's another view. This is the view of Atacama Desert close to this is the Parallel Observatory. Again, it's completely lifeless. There's nothing, almost no vegetation, just a rocky land, and absolutely beautiful sky. This is absolutely real. I'm saying I've been working there. It's funny things. But the Atacama Desert is different as well. So there are seasons there. So not every season is perfect for astronomy. And there are two distinctive places in Atacama Desert, what we call like north of Atacama Desert, from the border from Peru down to approximately a region of Copiapó here, Antofagasta region, where the Parallel Observatory is located here more or less. It's the north, and the best weather in this region would be in our winter, March to November. Remember, it's the southern hemisphere, so everything is very different now. So March to November, this is our winter. November to March, this is our summer. So in the south of the Atacama Desert, like where my observatory is located, our best weather would be now, like in Chilean summer. While in winter, the best weather will be just up in the north. And it also changes a little bit things for the observations, from the planet observations. In Atacama Desert changes as well. Like, look at this. So sometimes once in a while, just once in several years, it happens that the desert blossoms. Sometimes during the winter when we get like snow and rain, a little bit of rain, but just few drops of rain is totally enough to get the desert, all the flowers, they're there for like years and years and years. It can stand there for 15, 20 years, and suddenly when you get a little bit of water, bangs. So the whole desert just blooming like this. It's becoming absolutely surreal. Like suddenly the place which was like you would never guess there is something which can live and blossom and just suddenly just appears like this. So Atacama is beautiful, and if you come in the right time of the year, you'll be lucky to see this event too. Now, what I was talking about the sky transparency, and this is real. I did a test when I came to Hong Kong like a year and a half ago. I was really surprised to see the difference. So before my trip, what I did in my observatory, I just took a picture. This is a picture of the sun close to my thumb. And what you see around my hand, the sky is totally blue, absolutely blue. So if you just close the sun, everything is blue, amazing blue everywhere. While I did the same in Hong Kong, the sky, and it was a clear day. I was told this is like the best day in Hong Kong. It was February in Hong Kong. I was told like this is the clear sky we can ever get. Like, let me say, fine. So you see the difference. It's absolutely the same form, the same settings, everything the same. So what is different is you see the color of the sky, and what is this? The color, it's the aerosols. This is the scattering in the atmosphere. So you see why astronomers now we are going to Chile, because scattering means it scatters light not only the sun, but also the distant galaxies and stars. So in Hong Kong, even if you put like a mega meter telescope just right here and just switch off all lights, just forget, for example, imagine that Hong Kong, all lights off, you will still not be able to go as deep to see as faint objects as possible with this telescope. Because just conditions intrinsically in Hong Kong, they are not good enough for astronomy. Just forget about light pollution. It's just the conditions. It's too much humidity here. This ocean, all this humidity up in the air. Just anyway, just a funny example. Now, this is the example of now in Chile. So when you go to the professional observatories, you can actually see the stars which are sinking in the ocean. Like when all those stars, like the color is pretty amazing. It's absolutely like a light red going to the deep blue here. It's almost real. So at night you can see stars up to the horizon. So while here, I mean in Hong Kong, you will never see this. Your star will be sinking somewhere here. So while in Chile, and this is what this what I recalled before, said before, inversion layer. You see those are clouds. We don't really see the ocean because ocean is always covered by the clouds. So that's the difference. When you go like in Atacama Desert, you have to make sure that you stay in Atacama Desert, not on the coast, because once you go down to the coast, the ocean, it's going to be always cloudy because all these clouds are just about a few hundred meters above. Okay, so that's why it's kind of our protection. Astronomers, we always stay at a high altitude, about in this case about 2,500 meters. It's totally sufficient for us to be above the clouds to see this kind of images. And here's the image of taken on top of Serra Amazonas mountain. Now we'll be talking a little bit about how astronomers are looking, because I mentioned all these criteria, what we should use to look for the site for the new observatory. But now that's the real job. So how astronomers actually go and check the sites? Because it's one thing when you just look at the Google Earth and say, oh, this place should be really good, we should go there. But actually, before you go there, you have to make sure, before you build the telescope, you have to make sure that the conditions are actually good. So astronomers, there are special sort of astronomers and physicists called astroclimatologists. So those people that spend their life just going into different places on Earth, installing the specific equipment, and actually doing in a scientific research over the months and years, making sure and checking whether the conditions are really good for the observatory. It's called Astroclimatology campaign. And the results of this campaign is the report which tells all the parameters from the site, weather, various parameters, as well as the seeing, the conditions of the image quality. Remember, so the image quality should be really good. And in this case, this is how astronomers do. Typically, they build like a temporary tower. On top of the tower, there's a small telescope which works every single night or during several years. So the small telescope, what it does, that there's only one function of this telescope: to take image of several stars close to zenith, and then measure the diameter of those stars. So the smaller the diameter of the star, the better the image quality. So the image should be less blurry, as less blurry as possible. It won't be perfect, but the idea is to find the site which gives you the best image quality. So the stars should be pinpoint idea. And this is how it's done. Like it's about 5-7 meters tower with a small telescope, and this guy who is staying there somewhere in the tent, they're checking the parameters like for several years. Now, ideally, if you're lucky, like in Atacama Desert, you can drive on top of the mountain. So typically, as you saw from the previous images, landscape in Chile is pretty shallow. So on many mountains, including summits like 5,000 meters, you actually don't climb. You can just drive up to 5,000 meters. But in many cases, like this is the ideal case, but in many cases it's not really possible because there is no road or the mountain is a bit too sharp, and astronomers use a different approach, and this is real. So you see, they put a small telescope on a donkey and then just go up and trying to do the same thing. So no fancy equipment, no fancy cars. So you have to deliver everything on these poor animals. Yeah, that's how it works. After all, the result of all this study is actually this called image quality plot. The seeing, this is the parameter here, you see the number 0.5. So this is the image in so-called arc seconds. It's the angular diameter of a star observed through the telescope. The smaller the number, the better the image quality, the sharper the image. Let's say, for instance, the typical number from Hong Kong here would be something out of scale. while in Chile, this is the, and it's not just the number itself, it's very low. So what this number tells you in simple terms, so many of you, I know the amateur astronomers, right? So 0.5, it's close to resolution of, let's say, 30 centimeters telescope. So what you do, if you put 30 centimeter telescope, which is not a small telescope like this, on the ground here in Chile, in Atacama Desert, and you look at the sky, you will see image completely still. It will be absolutely sharp because your telescope will be, resolution of your telescope will be equal up more or less to the image quality. So which means in physical terms you'll be observing like from space. There is no difference observing from space or from the ground. So this is how sky in Chile is good. So the image quality is so good that essentially for small telescopes you'll be almost observing like from space. Now, a few words now what to do. So when we find the spot, and you need to build the infrastructure, because astronomers, we do not live in the desert, but we spend significant amount of our time in the desert. So there should be some infrastructure built. And in this case, this is the hotel for astronomers. It's called Residencia here at the European Southern Observatory. You see on the hill there are telescopes, and this is the place used for astronomers to live, because astronomers. Typically, most of engineers and astronomers, we work in shifts. You spend like 1 week on the mountain, and then you go back and you spend another week at your home, which is not in the desert. Usually, many astronomers here, they live in the capital of Chile, in Santiago, which is about 2 hours flight from this place, if you people look about by now. So, conditions should be good enough. And remember, look at this. It's desert. Conditions are pretty harsh. Like humidity is so low, sometimes humidity go down to like a few percent only. So which means when humidity a few percent only, your skin get damaged like within a day or so. So if you don't apply a special cream, your skin will be like full of like a bloody hand. You'll get bloody hand in 2-3 days. It's very, very difficult. It's a harsh environment. So the conditions for the astronomers should be good enough. And this is the view again from Residencia. You see the landscape? Again, it's like if I don't put anything like terrestrial, I put Mars, you will believe me probably. It doesn't look like Mars. It's absolutely surreal landscape, and I advise you if you have a chance, if you go there, you'll be absolutely fascinated. So this is the way how it looks from inside. So the European Southern Observatory, in this case, they built like a bunker, a huge hotel, which is called Residencia. They put, when you see the size of this bunker, the hotel, you can put like a few palm trees inside. It's so big. Also, the area inside, they support a certain level of humidity, which is comfortable for people, because otherwise it's dry. And there's all facility for astronomers, like a canteen, so it's like a first-class restaurant. You get really good food, everything is for free, so you can pay for everything. So the food is really good. And there is even a pool. And the pool here, it's absolutely real. You see, it's like a small botanical garden inside. And there is a real pool. And pool is not, like in this case, it's not a luxury, because if you think about this, when you spend so much time there, the level of humidity should be sufficiently good for your skin as well. So this pool have two functions. The first one actually is like a recreation, so you can definitely swim there, enjoy the pool, and on the other hand, it keeps also to contain the humidity. And you see, this is a roof made of glass here, and what you see on the right side, it's like a flower, it's a cover. So at night, when the night comes, this flower just goes all the way and covers the roof. So we protect the night sky from the light pollution coming from the hotel. So this is designed specifically to prevent the light pollution from itself. So astronomers that should care about themselves too. And this is the view of the typical control room from the very large telescope here. As you see, there's lots of people. In this case, very large telescope is controlled from the building adjacent to the telescope. It's located a few hundred meters from the telescope. There are usually several people sitting by the console. Everything is done now from the computers. So astronomers these days, we do not sit at the telescope. We are not looking through the eyepiece. We control everything from the computer. It's actually a serious question, because people ask many times, like, they still think about astronomers like this guy sitting in the ladder, just looking through the eyepiece. But usually we don't do this anymore. It's all controlled by computers these days. There are several people like telescope operators. Since the systems become so complex, there are several people who have to control the whole system. Like there is a person called telescope operator which controls telescope only, and there is another person which is astronomer who takes care of instrumentation, which just do the physical observations, click the buttons, and just take pictures of galaxies or other objects. The eyepiece is a large telescope. I said that it's almost like a joke. As I said, astronomers don't really do this. But there is one observatory in the world where you can look through the eyepiece through the 6.5 meter telescope. There's one place, and this is the place where I work. So now you can imagine, this is not Photoshop, it's real. So there's a bunch of visitors here, the delegation. This is the eyepiece put in the 6 meter telescope. And we observe in the sky, we observe the objects through the eyepiece. And here, it's even more that began a few years ago when we put so-called adaptive optics. I will tell it a few words later. So we managed to observe with the fully corrected optics. We were looking at the Alpha Centauri and the Saturn and a few other objects. We managed to see the telescope working at full potential, which adaptive optics, I will tell you later, just improve the image quality to the level of theoretical performance of the instrument. So we managed to do it a few years ago with Las Campanas Observatory. So this is the unique observatory in the world. So nowhere else you can do it. And the reason is very simple. It's not like for everybody. Everybody can come there and say, "Oh, I would like to see through the eyepiece." Unfortunately, it's not like this. So you have to. Las Campanas itself is a part of Carnegie. As you know, probably the Carnegie is a private, 100% private observatory. All money which comes to us comes from private donations. It's the model which Carnegie has been using for years. People who understand the value of fundamental science, they donate money, and we just use this money to conduct scientific research. So if you want to look through, people who look through the telescope, it's typically the scientists, like us who do science, or those who donate a substantial amount of money. So if you donated like $100 million, maybe you can do it. If you haven't donated yet, let me know, I will help you too. So people ask, like, what do you see at sky when you look through the 6 meter telescope on the sky? It's like a dream for many astronomers. So this is the image of the Eta Carina, the homunculus nebula. It's a supermassive star which is at the end of the life cycle. There's lots of ejection material from the star. This is the central object right here. So when you look through the 6.5 meter telescope, you essentially look at this object. This is what you see. It's full of colors. You see all the structure, but basically this is the image you might expect. This is 100% what I've seen with my eyes. The color, this is the image from the Hubble Space Telescope, but that's what I've seen with my eyes, and it was much more colorful than this. It was really impressive. So it's totally worth $100 million. Yeah, so anyway, now the question is when we do this research, since telescopes are incredibly complex machines, so here is the image of the 8 meter telescope, VLT, from the Isoclinic. And as you know, the main mirror, which is located right here, is an extremely delicate structure. When telescope moves, as you see, lots of things have reflection here. So now the question is, what are we going to do when the telescope goes from one part of the sky to the other? So what's going to happen to the primary mirror? It's going to be bending, distorting the image quality, because when you move the telescope, due to the huge weight of the mirror itself, the reflection of the mirror is unavoidable. So how astronomers deal with this? So this is the image of the primary mirror cell, with the mirror removed here, and what you see, there's lots of spikes here. So what are those elements? So why astronomers did it so complicated? Why we can just put single piece of glass on some kind of solid surface and try to observe the objects? And you will see the reason now. This is the mirror of the VLT. The diameter of the mirror is 8.1 meters, but the thickness of the mirror here it's about less than 20 centimeters, like this. So now we can imagine the diameter is like 8 meters, thickness about 20. So actually, if you put this mirror just on the surface and try to elevate it, it just breaks because it's so thin. And this is like it's a glassy structure, it's Pyrex. So what it does in the 70s, there was a new technology developed, which is called active optics. So astronomers in the 60s, realized that at some point we are reaching the limit of physical limit of the mirrors we can make, and the biggest mirror, solid mirror, we didn't have the structure, was the Russian 6-meter telescope installed in Russian Caucasus Mountains. So the mirror is 6 meters, but it's almost 1 meter thick. It was the only way how to make it solid enough and not to bend. So for beyond 6 meters was totally impractical now to build mirrors much bigger than 6 meters, and because the thickness would become like a few meters, so it would be totally impossible to make them work mechanically. So this is why I was designed a technique which is called active optics. So which means the mirror was decided to be extremely thin, but beneath the mirror now, we were put in the system of active supporting pillars, which were changing the configuration all the time. So the computer was attached to those pillars, and now the astronomers, when we go on the object, we are trying to look at the star. The computer was involved now. The computer was looking at the image of the star because the mirror shape is bending now. So computer was getting a picture which was totally horrible. And then using the specific algorithm, it was reconstructing the theoretical shape of the mirror and applying opposite forces to these pillars. They were changing the shape of the mirror, so it was dynamic change of the shape of the mirror now. So now, regardless where you go on the sky, the computer was always doing the analysis of the shape of the mirror and introducing forces to adjust the shape to its perfect condition. So this system is called active optics. And remember what I was telling you about the atmosphere. Now the problem is, even if the mirror now is perfect, everything is good, so you're looking at the sky, and this is the comparison. On the left side is the image coming from the 8.4 meter telescope, and here on the right side, the image is coming from the 40 centimeters telescope, 40. Okay, and as you see in terms of resolution, just look at the resolution, the images are pretty comparable. So you might ask me, like, how is it possible? How is the image from the 8 meter telescope, which should be much, much sharper, is not better than the image coming from the 0.4 meter telescope? And the question is the answer is the atmosphere. Atmosphere blurs the images to the level that at some point the diameter of the telescope doesn't make any difference. So in terms of resolution, we are limited not by the size of the telescope now, but just by the atmosphere. You can get infinitely large telescope, but its resolution will be limited by the atmosphere. So the astronomers need another technique trying to overcome the problem of the turbulence of the atmosphere and try to recreate the image in the best possible way, closer to theoretical performance. And this is called adaptive optics. It was a technique developed again by the military first, who are trying to use this technique to spot targets at very large distances because they were also affected by the atmosphere. But in the nutshell, I hope this will work. Okay, yeah, it works. So you see, this is the image of the atmosphere from the Untitled. Just wait a few seconds and you will see. Bam. So this kind of magic. So the first look, what we started, the first cloud, it was the image coming from the real telescope before the system was switched on. Then when you switch on the system, which does correction of with a very high frequency, this is what the normal conditions look like. Then suddenly when we start switching the active optics, the image starts to improve. And after a few seconds, you see, oh, it's going to improve. So in this case, the telescope now works on the theoretical performance. The image quality becomes really corresponding to what the telescope is designed for. So essentially in this case, we are like putting the telescope in space. So this is one of the technologies in astronomy which we are using to correct the image quality. And this is the result in the practical terms how it looks for astronomy. For instance, on the left side, this is the image of the galactic center, of the area of the galactic center. The galactic center is this is from the program, by the way. I was talking about the supermassive black hole in the center. This is the images which were obtained by the German astronomers to study the stars in the galactic center. So you see, without the correction of active optics, it looks, everything looks really blurry. Now, once we switch on the adaptive optics, you see, that's the same part of the sky. You see how much more we see. The telescope is like getting in of glasses. You start suddenly see everything in sharp light. So this is the active optics. It's a fundamental technique which we use now to resolve, to study our objects in very high resolution. The problem with the active optics, though, that in order to do proper correction of your image, you must have relatively bright star close to. For example, if you want to study this galaxy, take very sharp image of this galaxy, we need to make sure that there is a sufficiently bright star close to this galaxy, because active optics, adaptive optics in this case, it uses first the light from the star to understand how the wavefront, how the light is changing when it's coming through the atmosphere, and it uses this model to correct the shape of the mirror. Now, the problem is, if you observe, for example, distant galaxies, like in this case, they're extremely faint, there's no star at all. Look at this, it's the same field of view light, but there's no star. So in this case, if you don't have a bright star, it will be physically impossible to do any correction, because telescope doesn't know how to correct the image. So astronomers invented another technique. They said, okay, if there's no star, we are trying to create a new star. And how to do it? That's good. They use the laser. So again, coming from the military, it was discovered that in our planet, at the elevation about 90 kilometers in the upper atmosphere, there is an extremely layer of atomic sodium. And this atomic sodium layer comes from the meteors, which are bombarding our atmosphere like every second. So it was calculated, if we shoot a laser tuned with the wavelengths tuned to the excitation level of the sodium, so it's going to be 590 nanometers, 590 nanometers. Then in this case, we can excite this part of the sky, and it will start shining. So it was tested that if we shoot this extremely narrow beam of laser with the same wavelengths in the upper atmosphere, we will get a spot. In this case, the spot is a bit elongated, but this is the idea. It was shot laser up there, and this is the image of the VLT. Large telescope with the laser is shooting close to the galactic center. And once we create the spot, this is another image of the VLT. Once we create the spot, you see close to Saturn. So in this case, we suddenly create an artificial star close to Saturn, and now we can use the camera with adaptive optics to get extremely sharp images of the planet in this case. So that was the fundamental breakthrough in astronomy, using these adaptive optics to create absolutely sharp images of celestial objects like planets or galaxies. Now, these days, we actually went beyond this. One laser was not enough, because unfortunately, in order to create sharp images on a sufficiently large area of the sky, one laser beam is not enough. In order to cover the spatial variations of the image quality, you need to create several reference sources around your object of interest. Like in this case, VLT was upgraded to the system of 4 lasers. Now, in the field of view, you get 4 lasers creating 4 different stars, and those different stars have been analyzed at the same moment, and then reconstructing the image inside up to the highest quality. So this was the idea. And here the top secret stuff. I talked about this before. Top secret stuff, what it means. Several years ago, when I used to work for European Southern Observatory, we received a proposal from scientists in Europe. They were trying. It was some kind of date about NASA launched, I think, one of the lunar probes. The idea was to test technology of the VLT to see whether Americans actually landed to the moon. It was not a joke. It was a real scientific proposal. It was written in few pages of scientific text. So the idea was to use the capabilities of the VLT to look at the moon's surface and to see if they still don't believe that Americans went there. It was maybe staged in Hollywood. Okay? So what we did, unfortunately, the size of the model is it's still small. It's like a couple of meters. But Europeans were really smart enough. So what they did, they calculated very specific time when the sun will be rising here on this side of the moon. When the sun illuminates the model, which is supposedly should be on the ground, the model will produce a shadow. And then the size of this shadow will increase the resolution of the telescope. So which means if you manage to detect this shadow on the moon surface, you can say, yes, the model is there. We don't see the model, but using the shadow we can see the fact that it is there. So what we did, we went with the VLT at this very moment, calculated by the European astronomers. We looked at the surface of the moon using the adaptive optics system. We looked at the very predicted place, and we saw nothing. This is not a joke. We saw nothing. So there was a moment of silence in the control room, like, I don't know. But after all data analysis and lots of scientific investigation, we basically said that the conclusion was it doesn't actually necessarily mean that the model is not there. So there was there was amount of uncertainty in the calculations. So probably the length of the shadow was not long enough, so we still probably couldn't even see possibly. Or maybe the illumination, the terrain of the moon was not calculated properly, so we still don't know the properties really well. So the angle of the sun was probably not the same. So there are too many uncertainties, and the conclusion was maybe it's still there, but we were just wrong in our theoretical assumptions how to calculate properly the parameters for the search. So still open question. Okay, but then you can say, oh, but Americans, they sent another, spaceship which was orbiting the moon, taking many pictures. But the counter argument would say, but it was still an American, right? So the Americans can do what they want. They can paint on top, say, yeah, we have something. Anyway, so Europeans still don't have an idea what Americans landed to the moon or not. Okay, and I would like to conclude now with the future projects. So what we are doing in Chile now. So the next generation, the large telescope which are coming to Chile in the upcoming actually decade. This is the relative size of the mirrors of the telescope. It's 8.4 meters here in mirror, and then it goes upscale, 24, 30. So those actually, the project number 3 goes in the so-called TMT 30-meter telescopes going to the northern hemisphere. But those 3, large Synoptic survey telescope, Giant Magellan telescope, and an extremely large telescope, European telescope, those 3 telescopes are going to Chile. So those observatories selected Chile is the best site for their project. 30-meter telescopes goes to the north because, again, it's done by the United States and different observatories collaboration. And it makes sense for astronomy to have a synergy of have big telescopes in different hemispheres. So you can look at different objects. But this is the timeline now of, not the timeline, but just the size line of the telescopes. And I will briefly say why we need to go with such a large size. At some point now we got stuck with the current instrumentations, current telescopes. We got stuck that in order to study extremely faint objects or extremely small objects like extrasolar planets, to study the chemistry of interstellar media, to study the nature of the dark matter and dark energy. So we definitely need to go deeper. So we need to see extremely faint objects. So which means using current instrumentation, it might take tens of years to integrate the light in order to get information. So the bigger the size of the telescope, the faster we can collect the lights, the more light we collect. So building a bigger telescope, it's not like, because we need to get a fancy telescope. It's essential because we need more and more light coming in the second of time to the surface of the telescope. And this is why astronomers from various countries built up now teams to go after such ambitious projects. The thing is, this is the scale, how it's going to look like. This is the Colosseum in Rome, and this will be the size of, in this case, future European extremely large telescope, where the dome will be hitting the limit with 100 meters here. And this is for the comparison, the size of the existing domes of the VLT. It's 8.2 meter telescopes. You see, those telescopes is going to be one of the first, the extra big telescopes, the large telescopes. That's the scale. Now, for the comparison again, put the existing 8-meter telescope and put it next to the future ELT. This is the relative size. So it's huge. It's going to be an enormous machine. And in numbers, the future mirror of big telescope, of ELT, is actually going to be segmented. So there will be no solid mirror. Instead, the primary mirror will consist out of the about almost 800 hexagonal elements, spherical hexagonal elements, like a honeycomb here, where they will be collecting the lights and sending into the secondary mirror, which will be solid, 4.2 meter diameter mirror, and sending it back into the instrumentation behind the primary mirror. So this is the optical design of the telescope. And the effective diameter of the telescope is going to be 39 meters. Now, You remember the biggest telescope on Earth now is about 10-meter telescope. This is the size. So the 39 is almost factor we see by 4 just in diameter. Now the idea how it's going to be done, this is the timeline. So this is the mountain was selected close to Cerro Paranal in Chile. The road was built, so now the phase 2, they completed the cleaning. You see what astronomers do, we cut the mountain in order to make a foundation. And this will be the process of constructing the dome starting from the 0 up to the finished structure. This is the real-time image now obtained just a few months ago from Chile. This is how the stage is. You see the road is almost done, and now they're digging the foundation for the telescope, and this you see the landscape around. So the telescope expected to see the first light around 2025 maybe. So if everything goes well, typically this kind of project, cost of the telescope now, keep in mind, of each of them, is going to be close to between $1 and $2 billion. Close to. So those are very expensive projects. Of course, it's still lower than the cost of the space telescope. Like the cost of Hubble Space Telescope is close now almost to $10 billion. So, but this one is definitely cheaper, but it will be much more efficient than space telescope in this case because of the collecting area. And that's the rendering like how it's going to look in the future, because of course all those telescopes, they will be equipped with a system of adaptive optics with the supporting lasers shooting in the sky, creating the artificial stars which will allow us to how to correct wavefront and to get as sharp images as possible. Another telescope I mentioned was that it will be the Giant Magellan Telescope, which will be constructed on the site of my observatory, Las Campanas Observatory. We have the mountain next to Magellan telescopes, just a little bit higher. Unlike European telescopes, you see, European telescopes will be the honeycomb of 800 segments. The GMT, it's an American project led by Carnegie. Approach is a little bit different. So instead of making lots of hexagonal segments, it was decided to build like a 7 hyperbolic mirrors, is off-axis hyperboloids here. So which essentially the idea is the same. They reflect the light in the secondary mirror and then send the light back to instrumentation. It's a very different approach. There are many reasons why Americans did it this way, but it's kind of beauty of science because there are many things can be done in different ways. The result will be the same. Effective diameter of this telescope is going to be smaller. It's close to 25 meters here. But essentially the scientific case will be the same. We're going to study exactly the same problems in the universe. And this is just the relative result. For instance, here is the diameter of the future JWST space telescope, which will be sent to space hopefully next year. And this is how it relates to the diameter now of the GMT. So it's going to be truly a large telescope, and that's how it works. So the light reflects from each mirror being sent to the secondary mirror, and then goes into the hole inside the mirror number 3 into the instrumentation. And now this is the process how we do these mirrors, because what you see here is the pile of glass. It's a pile of glass in the oven. You know, the workers are putting manually, every single piece of glass is put by hands into the oven, into the special shaped container, which is then goes into the oven. And the glass will be melted. When the glass melts, it will start to rotate to make it more uniform. And then the cooling time takes several months just to cool down the whole, because it takes real long time to process this glass because of we have to make sure first of all the glass is uniform, and secondly the cooling must be extremely slow to keep the tensions inside the glass up to the minimum, so the glass will not break when you cool it down completely. And this is the Arizona Mirror Lab where the mirror is done. And here is the process. This telescope is actually being constructed now. The mirror number 1 is completely ready. It's done. It's polished. It's ready for the secondary mirror is being polished now and controlled. This one they just finished melting the glass and just got glass ready for processing. And then for the other mirrors, they just purchased the glass and they started to melt. So probably if everything goes well, the Giant Magellan Telescope might be the first telescope in the Southern Hemisphere if it goes well. And the project number 3, it's a large Synoptic survey telescope. It's very different from those two telescopes I mentioned before. The diameter of this telescope is only 8.4 meters, but the function of the telescope is going to be completely unique in the cell of the telescope in the southern hemisphere. Instead of going really deep, studying the adaptive optics, studying extremely faint objects, this telescope, its function to go really wide. So since it's a survey telescope, its function will be to survey all the sky during the night. So it is such an 8-meter telescope. The camera itself is 3 billion pixels. It's going to be the biggest astronomical camera ever. And it will be generating like about 30 terabytes data per night, because it's going to be scanning all the sky in this case. This is the optical design, extremely complex optical design, which involves 5 mirrors, very complicated. This is the camera with the filters. And here you see the field of view. So this is the size of the moon. It's about half of a degree size of the moon. So you see in one shot, this camera will be able to cover an enormous portion of the sky. So the scientific goals here are pretty much similar, but a little bit still different, because in this case, on the larger scale, we'll be trying to find comets, asteroids in the solar planet. We'll be able to trace the transient events in the sky, like supernovae, hypernovae, or gamma ray burst. And we also will be trying to study the structure of the universe on a much bigger scale to get better understanding of the dark matter and the dark energy. And the last thing I wanted to mention now, that the Chilean sky is much closer than you might think, because I was talking now about the professional astronomy. I wanted just to mention a few amateur astronomers, because as you know, like in Hong Kong, the conditions are so bad now. All around the planet, the conditions are getting really bad. I mean, there's a lot of light pollution coming, other pollution is coming. So if you're still fond of astronomy, if you really want to do some kind of astronomical observations, it's getting really difficult to do it. So over the last years, there have been done many attempts to make the sky more accessible to people. And there are various teams of like amateur astronomers. They started to build what we call like remote observatories. They start to build observatories like in Atacama Desert, giving people access through internet to the telescopes. In this case, I just mentioned one project which we call Chile Telescope. It's a project which was started in Chile just a few years ago. A couple of enthusiasts, they put 1 meter telescope, is the size of the telescope, 1 meter telescope on the area close to the Gemini Observatory. The observatory consists of the dome of 1 meter telescope and 3 domes with half-meter telescopes right there. So that those telescopes are equipped with the state-of-the-art cameras. You can access planetary camera. There is a planetary camera for the imaging of planets, and the CCD camera for doing imaging of the deep sky images. These are the astrographs right there, so you can do it. And few images just to show the potential of the instrument. These are very fast instruments. You can simply log in through internet, check it out, and there you go. Thank you so much for your attention. If you have any questions, feel free to ask. Yeah? Oh, yeah.
Mr. Belinsky, I'm a lover of astronomy. Everybody knows we live in the solar system, and the sun is the center of our solar system. The sun is a star, and there are 8 planets in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Our solar system belongs to the Milky Way galaxy. The Milky Way galaxy is a big place. The diameter of the Milky Way galaxy is 100,000 light years across, and there are many stars in the Milky Way galaxy.
Yeah.
There are 300 billion stars in our Milky Way galaxy.
Okay.
And the Milky Way galaxy is just one galaxy.
Yes.
Astronomers use large optical telescopes to observe the universe. There are 200 billion galaxies in our observable universe.
Yes.
Many astronomers ask the same question: are we alone in the universe? I want to ask you, Mr. Belinsky, your personal opinion. Do you believe intelligent life in the universe?
Absolutely, yes. Absolutely. Well, the thing is, again, our planet, we know now for sure that we are not unique. I mean, the conditions, and we're speaking about just Earth-sized planet. I mean, I just, for a second, just forget about it. There might be forms of life which can live on the big planets like Jupiter or Saturn or anything like this. So, just speaking about Earth-sized planet, we know that statistically there are billions of planets like this in the universe. So we are not unique in the statistical sense. So if we are not unique, we know that there are planets with similar conditions, so there should be life, because again, the evolution we know tells us that this kind of form of life can easily appear somewhere else. So yes, my answer is I believe that we are not alone. The problem is just we don't really know where the other forms of life, which planet. We cannot pinpoint the planet yet to say, okay, this planet has life. So now this is the goal for these big telescopes which are being built now in Chile. So we, using those telescopes, we'll be able to probe the conditions on those very planets and to say, oh, this planet with the probability of, let's say, 80–90% might have a life. So this is the goal for those telescopes. So I believe we are not alone, but another question whether you want to know whether you're alone or not. No, because it's a philosophical question, because if you think about this, many people don't really realize, so what happens if we find out we are not alone? So what do we do? So any civilization which will approach us, by definition, should be much more developed than us if they manage to get here to see us. So now the question is who we are for them. It could be like a box, because we will be, from their point of view, we will be absolutely undeveloped. We will be totally like insects for them. So they can just wipe us out like completely, or they will simply ignore us because they don't have anything to talk about. Because they're so much higher developed, they have nothing to exchange. People are naive. I think we think like, oh, if they come to us, they will start talking to us. But the answer is not obvious. Like, why should they start talking to us? Because they're so much more developed. And especially looking at what's happening in the world, they actually will think twice. Like, why do we need to give any technology? They're killing each other without, any help. So that's why it's not obvious. But we are not alone. It's my personal opinion. Oh yes, please. Yeah.
Just a quick one. About building microscope, I cannot help noticing earlier in your presentation that there's a light pollution now, and I can see that our Beijing area, the light pollution is actually quite severe. Yet and still there's a microscope building there, a large one. So
Telescope.
Yeah. Would you like to comment on that?
The area close to Beijing, right?
Yeah.
Yeah, there is a telescope which is called LAMOST. It's very famous. It's one of the biggest Chinese probably biggest Chinese optical telescope. I'm not talking about the radio because China has now the biggest radio telescope in the world. Yeah, it's different. So scientifically, it's a good question. I can't really comment much because there hasn't been much of the scientific results coming from this observatory, and the explanation. When the project was started, again, it's just my personal opinion, so I don't know the facts, what's happening inside Chinese astronomy, it's very difficult. I know there have been some technical challenges, because building a telescope of 4-meter class, it's very difficult. So you can easily, when you mention astronomers, when you make a telescope 10 centimeters and 50 centimeters, it's pretty much just upscaling just a little bit, it's a little bit more work. But when you upscale telescope to a few meters, the problems just grow exponentially. So you should have a sufficient amount of know-how and technologies how to overcome those problems. So China at that point was not ready to do it. So, and I think they're getting there. The light pollution is a bit, I think, an issue. The air pollution is well an issue. I don't know. It was probably more like a political decision to put rather than rational based on. But remember, that's the thing. It's very difficult. I said I don't know the exact situation about Chinese observatory in that case, because for lots of research, you can actually still do lots of science from light polluted areas. For example, the study of hydrogen study of the planets, when we just need resolution to use so-called lucky imaging. Probably you don't need really good sky to study many of just chemical composition of stars, for example. So you can study relatively bright objects. So light pollution is not really a big issue. So the point is, you always can find a scientific project adjusting to your local conditions. So you cannot do things like you do in Chile, in China. Yeah. Tibet is a much better place. Western China is a much better place for this. There are other difficulties there. The altitude is about 5,000 meters pretty high. Sky is different, but yeah, sight is much better. Western China is definitely better sight for astronomy. And there are projects there, so it's.
Mr. Belansky? Yes, my question is, can you explain a little bit more about the difference between imaging by the adaptive optics by just one laser and several lasers?
Yeah.
What's the major difference and more?
Yeah, the major difference is there is a term which is called Isoclinic Angle. So which means when you have an so-called reference image of a star, which you use to correct the wavefront, you can correct image quality in the very small vicinity of this star. And usually this size is about few arcseconds only. So which means if you want to get an image of larger than few arcseconds, let's say 20 arcseconds, or even half a minute, so the correction which laser shoots the image, correction which is done based on the star will be quickly decreasing the quality correction towards in the radial distance. So the further you go from the reference source, the worse the image quality is. So at some point the correction will be so poor that basically there is no correction. So now, in order to increase the area, so you need to create like in this case, 4 reference stars in the corner of the quadrant. So in this case, you can increase the area, and you can correct using those 4 stars simultaneously. You can now fully correct within the rectangle, which is much bigger than a few arcseconds. So the only reason for having several lasers is just to increase the area where you can correct the image. That's the only reason for that.
That means the created stars just circle around the
Yes.
image, okay? Just
Exactly. You just put it not necessarily a rectangle. It can be a circle. Whatever. How many lasers do you have? Which is just up to you. So essentially, that is you surround the area of interest with the laser spots, and then use laser spots to correct everything which is inside the area. Oh, okay. Yeah. Okay. Let's.
I want to ask is the observatory has a tourist center that let people to go in and visit? You know?
That's a great question. Absolutely amazing question. Yes. Well, in Chile, the biggest observatories like Paraíso, European Southern Observatory, and the Gemini, they do have a visitor centers where you can go. And actually, at BLT, it's free of charge. They have one day per week. It's usually Saturday. So where organized group can go like in the bus, and you will get excursion on the telescope. So they will show you the telescope during the day. The only problem there, you will not be allowed to stay there at night. So none of the professional observatories in the world allow people to stay at night, unfortunately, because just to minimize the impact of tourists on scientific observations. So that's the limitation. So unfortunately, staying at night it's pretty much no. But at least you will see the instrumentation.
Can we put a telescope remotely at night?
Remotely?
Yeah. I mean, no person present.
Yeah, if you have enough money, you can do it. Again, it comes to money. You can just buy a piece of land or just.
No, I mean a mobile system.
Mobile system.
Yeah, a small telescope. Can we put a small telescope?
And then go.
Yeah.
No, I don't think so. No, well, as I said, if you donate millions of dollars, then they probably will allow you to build your own telescope. Probably not even the case. Yeah. Because the observatory, as well, as I said, observatory first goal of the official observatory is just scientific investigation. So it's not just a place where people can come and just build something. So we have examples of people with money approaching our observatory and saying, okay, I would like to put my telescope, and like this is the money. And the observatory still says no, because they do thorough investigation, who the person is, what are the interests and so on. So it's not easy. So it's not enough to have money. You should have something more than that. So
More serious question. What percentage of the observations are remotely triggered, like by the GW 1708, 1708?
Well, again, it depends on the observatory. Like for example, our observatory Las Campanas, we do not offer the possibility at all, because Las Campanas works in 100% visible mode, so the astronomers come to the telescope and sit at the console to do their own observations. Paranal, Paranal and Gemini, they do have a special, they call Q mode, when it can be triggered. So in Paranal, I think, as far as I remember, they spend something like 60% of mode where observers are not required to be at this side. And there is a certain amount of time which also dedicated to the triggers. It can be, but again, it varies from semester to semester, this amount of time. Yeah. In principle, there is a special mode which is called rapid response mode, where if you want to study rapid events, like for example some supernova just explode or something like this, so some astronomers can trigger the observation in real time. So which means like if you're sitting in your office and you suddenly something happens, you click the button, and then whatever happens on the telescope just stops, and telescope goes in the sky, start observing. Yeah, it's only Paranal offers this possibility.
Thank you. And I guess this is we'll stop here because we have another section. Maybe we'll let you return take for a while.
Yeah, you can ask me questions just off the just here. Yeah. What time are we starting? Okay. So we have like 5 minutes, but in these 5 minutes you can just come to me if you have any other questions. I can answer just. Real passion was astronomical photography and nightscape photography in particular. So it's not just photography of the celestial objects, but it's something which includes the foreground. And here today I will just tell you in a bit more in details about my hobby, how I do it, how I came to it, and hopefully, I might inspire one of you just to do the same, just to go outside and take some pictures, because some of them are really interesting. So here I just want to start quickly describing what I will be talking about. There are two things in this type of photography. One is called like Astro Photography, which we assume we are taking pictures of the so-called deep sky objects like nebulas, galaxies, cluster stars, where the object essentially is something which is located on the sky only. And we usually use telescopes for this purpose, or like a wide-angle lens, anything. Image includes only the sky. Now the second topic is the nightscape photography, which includes a night sky and the foreground, which is something on the ground. So I will be in this presentation, we'll be focusing mainly on the nightscape because it's much more accessible for majority of people, because typically for astrophotography you need a bit more sophisticated and expensive equipment like telescopes, mounts, CCD cameras. It can be, it's like an avalanche. The price of this hobby goes up very quickly. So let's talk about nightscape photography.
No problem for you.
And first of all, before I do start talking about technicalities, I would like to talk about imaging philosophy. I always do this in the beginning of my talk, just to give you an idea what I do and how it's different from maybe other images you might see on the internet. Because these days, if you just open Instagram, Facebook, whatever, you see tons of images of this beautiful galaxy, this incredible Milky Way in front of whatever. And at some point, if you start to go into the topic and try to understand how these images were taken, you will pretty quickly realize that many of them are not real at all. It's just, it's people use Photoshop skills to just produce amazing images, which doesn't mean anything. It's wrong. People are creative, and I totally think it's absolutely fine to do. I was just going to say that my philosophy is, since I'm an astronomer and my imaging has been always about more like a realistic approach to the sky, I show people the moment which I experienced when I was in this particular place taking this particular picture. And I will explain what I mean now. Now look at this image which I took in Sweden. You see this beautiful Milky Way, with this amazing foreground. And when I publish this image, people say, oh, this is really amazing, beautiful sky, just incredible, right? And then I published another image saying, look, I have another even better one, like this. There were horses, just running in front of me in my camera and in front of the Milky Way. People said, oh, it's even better image, it's really cool. The only problem here is, it's a joke. I mean, this image, if I didn't tell you before, I told maybe someone understand. I said I obtained this image in Sweden. So Sweden in the northern hemisphere, and what you see here is the Milky Way, which corresponds to the southern hemisphere. So this is pure image manipulation. It's Photoshop. It's unreal. So this is my image taken from Atacama Desert. And this is the foreground, was taken by a very good friend of mine, professional photographer in Sweden. So we just, made a joke, said, okay, let's see how people react. This is the problem is, if you have sufficient proficiency in image manipulation tools like Photoshop, Lightroom, whatever, so you can pretty much do whatever you want these days. So if I didn't tell you it's fake, people will say, oh, they'll give you like thousands of likes for this image, it's perfect, it's amazing. And the other one, if you say people, oh, I saw the horses running in front of the Milky Way, no, you're laughing, but many people actually don't realize it's fake. They'll say, oh yeah, show me the place, I want to go there and just tell me it's fake. Yeah.
Beautiful landscape.
So my point is, the bottom line is, those images might look really incredible, amazing, but they're totally unrealistic. Absolutely, it's a fake news, as some presidents say. Now, this is another kind of extreme. We go to another extreme, since like being a scientist, and some people, when it comes to imaging, you'll be surprised if any of you is like a photographer, more like a serious photographer. You probably encountered people in your life who are taking photography so seriously, and they think like everything which comes from the camera should not be changed at all. Okay, so no Photoshop, nothing. So image should be absolutely real, and nothing should be done to the image, otherwise it's fake. So this is an example, like it's a raw image from my camera taken at Observatory in Chile, and you see it's almost black and white. It's completely kind of dark, and it's honestly it looks totally like a boring, Scientifically, it's accurate. Nothing has been changed here. Nothing was added. It was just a straight image from my camera to Photoshop, and that's basically the result. Now, there is a bigger question here. In photography, this type of photography, what is real, what is not real? Or in the other way I like to describe it is art versus science. So science, as an example, we don't change anything in the image. Art, we can do whatever we want with the image. So many people trying to find the balance, and from my point of view, actually, there is no like a right and wrong here. It's totally up to you. So nobody can forbid you to do this. For example, if you want to do this crazy composition, I say it's fine, just do it. The only question when it comes here on numerous forums or Instagram, when people start to fight about what is real, what is not, is just honesty of photographer. If photographer is honest and say, okay, what I've done is not real, but it looks beautiful, I think nobody has a problem saying that's your creativity, right? So I will never see Milky Way in Sweden in this way, but I like how it looks. So I will do it, and I say, okay, this is image, it's not real, but I like it. It's fine. The biggest problem when people start to cheat, especially in the various competitions, when you submit the image somewhere and you try to say, oh no, this is real, but then of course it's not. So this is the biggest issue. So my take on this, I think any type of creativity is fine as long as you're honest with the audience. As long as you say like this image was obtained in this way and you don't try to cheat the system, I think anything you do is good. So here, before we start again, few important definitions what I will be using in photography, which I use in photography. So just to explain a few types of images of the Milky Way or nightscape images you will see or you might see on the social media or on the media in general. So the first class of images we call like a single images. So what is single images? Single image, it's suppose that you just take an image with your camera. This is like an example of single image. It's some people observing with the Dobsonian telescope, and I just put my camera behind. I did like a one snapshot, in this case with like a 30 seconds exposure time, just one image. I took it in Photoshop, just played a little bit with the various adjustments. But it's a single image, nothing was added, nothing was subtracted. It's just one image with a little bit boost of colors. This is a single image. The second class of images, which I call blend images, what I call blend. So what is blend? The biggest problem in nightscape photography, of course, is the lack of light. So it's not a problem like a conventional photography. When you walk in the streets of Hong Kong, you take a camera, click, 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 you get like a perfectly exposed image, and you can just print it almost right away. In astronomy, unfortunately, we're working at night. There's always a problem with illumination, not enough light, so we need to do something to increase the exposure times. That's why in order to get really nice picture of the night sky, we should expose seconds or tens of seconds or minutes in order to get enough signal. In this case, when you expose for for tens of seconds or for minutes, now we have a problem with the rotation of the Earth. So the Earth rotates, so which means like in like a 20-30 seconds, depends on the focal length of the camera, the sky will move, and the stars will not be pinpoint anymore. They will be like a streaks. So you have to somehow compensate for this. And this is an example of the composite image. Like this is the way when you shoot the foreground and the celestial objects in two different exposure times, and then you combine them in one single image. So technically what you see here is not a single image. It was not a camera pointed in the sky and clicked. No, it was one single exposure for the foreground, because you see this, the foreground is pretty sharp, this tree is out of focus, but then you see the moon and the comet. Here the problem is the dynamic range is so huge of the moon that in one single exposure, no way you can get such a sharp image of the moon and not saturated, and especially the comet. The comet was so faint that it's not possible to get this image in one single exposure time. So in this case, it's a complicated, what I call blend, when you combine like three different scenes here, taken from the same place. You take a foreground, then you took the moon and took several pictures of the moon with different, very, very short exposure times and combined them. And also at the same time after that, you took several images of the comet. I mean, taking the same locations and you combine them too. And this is the blend of like about 10 images in total, probably, as far as I remember. So combined in the one scene taken from the same place. So technically, scientifically, this is a correct image, because this is how it looked at this very moment when I was taking a picture. But I used different techniques. I combined many images over the course of like several minutes, and this is the result. So for many people say, oh, this is fake image because it was not taken in one single shot. But in this case, scientifically, we're still accurate. This is what is called blend. So blend, when we combine images taken from the same location with the same equipment, but using just different exposure times, just to overcome our technical imperfections of the camera. And the composite. So what is the composite? The composite example you saw just before. The composite, which you just combine anything you want, however you want. You take like image from one side and attach sky taken from the other side, and this is what we call composite, because we're composing things which are not real at all. This is an example. Yeah, so this is it's Hong Kong, beautiful, and this is the sky which you will never see, ever see. If you switch off the light of the whole city, and the sky will be perfect, you will never see this, because this is the southern Milky Way. I mean, all this part up here on the left. No, actually, yeah, from here.
That's incredible.
Southern Cross and Alpha Centauri, it's impossible. Yeah, so this is what we call composite, right? Sky taken in Chile and the image taken here in Hong Kong. It looks beautiful, perfect, but it's not real. So again, as long as you're honest with the audience, I see no problem. You can. I usually don't do these images at all, because in this case I just made it as an example, just for you, just to show what is real, what is not. But normally in my practice, I don't do this kind of images. It's just I prefer to do something which is more realistic. And then the fourth type of images is panorama. So what it means is, if you want to take a picture of the large part of the sky, so technically with one single lens, it's really impossible to cover like the whole, like a 180 degrees. Like in this case, you get area covered by 240 degrees, I think. It's the Isoclinic Observatory in the Atacama Desert. And what we see here, the arc of the Milky Way, and those beautiful colors coming from the air glow. I will explain later what it is. So in order to get this image, it was obtained using like the same camera, same lens, which was set up at different angles, and it was at least something like 10 images taken just consequently one after the other, and then they were combined using the software. So scientifically, this is a correct image, but again, this is not a single exposure time. It just stitched from many images taken across the sky, just one after the other. So this is called panorama. Panorama, I do panoramas quite often in order to obtain this kind of effect because it's really beautiful. I like the arcs of the Milky Way. And I would like to mention the organization which I'm part of. It's called TWAN, the World at Night. It's an organization. It unites the photographers around the world from different countries. And our goal is to produce the images of the night sky to increase awareness of people about the importance of having unpolluted light sky in our lives and to preserve the night sky for our future generations. Because you see, from the previous talk I was showing the plot where the light pollution is constantly increasing on the planet. It's getting very difficult to get pictures. And we've got here a few examples of what we do. We just take we take pictures at different locations in different places with the goal of just promoting the culture of the night sky and preserving it for the future populations. Now, the challenges in night sky photography. Of course, for night photography, clear sky is essential. See again, Hong Kong versus the Atacama Desert. In order to get pictures of astronomical pictures, you must have some kind of clear sky. At least you should see a few stars, because if it's totally cloudy, it's just a nighttime photography. I mean, there is no way you can do something. So you should be lucky. That's why night sky photography is much more challenging, because it's not enough to go to location. You must kind of make sure that you get at least some chance of clear sky at the location to get some images. The light pollution. Light pollution again is becoming a really serious issue, because the more artificial light you get, the less stars you see. So it's becoming less and less. You're becoming less productive in getting beautiful images, because you simply lose the ability to see the Milky Way and beautiful stars. And it's one of the examples from like Austria in this case, when you climb the mountain next to the big city, and then you still see some stars, but the sea of lights, artificial lights, is just killing the composition down there. There is a scale for estimation of the quality of the darkness of the sky. Starting from the scale of 1, when it corresponds to excellent dark sky, when you see the Milky Way and stars up to the 6 magnitude, and up to probably what we see here in Hong Kong, scale 9, when you see just very bright stars, maybe the brightest stars you can possibly see on them. Now, I was showing the talk before. So this is the situation with light pollution in Europe. It was in 1999, like 20 years ago. So this is the prediction, what we might get in 2025, 2030 maybe. So the red light corresponds to the worst pollution, like in the middle of the city. So you see it's by 2025, pretty much all Central Europe will be unsuitable for good astronomical observations and for taking nightscape images without possibility of seeing the Milky Way. So that's the biggest issue. That's why now, even just not forget about astronomy, just taking it now, just a beautiful picture of the night sky requires you some traveling somewhere. The area is free from light pollution. So here in Hong Kong, of course, you know better. So in terms of, I will just repeat here the image of world at night. So this is distribution of the light pollution on the planet. Actually, it was taken like years ago. Now it's getting worse and worse. You see some areas like east of the east coast of the US, Europe, pretty much the whole Japan and just Southeastern Asia. It's kind of becoming hopeless for serious astronomical observations and for taking pictures as well. So that's why more and more people now start to traveling around the world. If you're a big fan of this astronomical imaging, so you're kind of forced to go somewhere to places which have much less light pollution. Also, the dust and aerosols is the problem. Well, what you see here, it's my hometown. It's Santiago de Chile. It's the capital of Chile. Those mountains are pretty high. They're like 3,000-4,000 meters. Santiago is just like in the valley, just in front of those mountains. You see the amount of light pollution is incredible. And the picture was taken from the hill in the center of the town, in the city. So those aerosols, it's coming from the pollution from the cars. So it's taken and it's it's pretty serious. I mean, in Santiago now there is huge struggle with trying to restrict the amount of cars on the street because it's becoming really, really difficult. So what happens is if you try to take an image being inside the city, even if you forget about the light pollution for a second, you switch off the light, so you will see your sky will not be brilliant enough. You know, it will be like a muddy sky. You will take a picture through this huge layer of dust. So your Milky Way image will be pretty blurry and colorless because of the huge amount of scattering in the atmosphere. So you really want to avoid big cities, not because of the light, but also because of this huge pollution, unfortunately. Now the weather, of course, when you do images at night, so you have to make sure the weather is good. So in this case, even in the mountains here in Chile, we have really harsh conditions sometimes. This is an image I took from my observatory where I work, where the thunderstorm was developing over Argentina. So you see lots of lightning at night. So we were very lucky in Chile just to see it from the outside, but over Argentina, if you go on the other side of the mountains, you will be probably completely in the clouds. So you really, before you start taking images, you make sure that you go to the area which has a good weather. And in this case here, just the same storm. I'll try to do the time lapse and see. Yeah, this is how it looked during the night. So can you imagine if you just on the other side? This is in Argentina. So if you just happen to be there, it will be like a big trouble. It's lots of rain. So, and this is a perfect example of the Chile climate. So as I mentioned in the talk before, most of the clouds usually stays on the other side of the Andes mountains, while when Chile has an absolutely clear sky, in Argentina just is full of thunderstorms and this type of clouds. So they're just on the bad side of the mountains. So the photographic equipment. What kind of equipment? This is the question which I get all the time. So what kind of equipment do I need to take a picture of the night sky? And my answer is pretty much any equipment, any camera. I'm just giving a suggestion like any full-frame camera. It's not like a guideline just to buy these cameras. It's changing, the technology is changing all the time. It can be anything. But what I'm saying is I would like to emphasize that this is important. In order to take images, go and take images. This is how we start doing things. Many people are just trying to buy the most expensive cameras and lenses and saying, okay, I've got the best equipment, I will get the best image. No. What you need to do, you just need first dedication and desire to learn. Because unless you're dedicated, unless you just go somewhere and try to do something, you will never succeed in anything. So again, my advice, go, even if the sky is not perfect, it's not like a Chile here, so still try to go to somewhere at the areas with the less light pollution, and even in light polluted areas, try to do something. Once you get into the mood taking images, you will learn how to process them, and the best way to get the best results, you just do it, it's practice. It's like, none of us was born to be like a genius in taking these images. We always spend some time learning how to do it. So just do it. Just go, take some images, learn, ask questions, because there's lots of now engagement groups on Facebook, Instagram, Twitter, WeChat here, right? Even I have WeChat now, I think. So I was forced, to install it, to talk to Chinese audience. I'm sorry. So, yeah, that's the best thing. Again, it's the best advice I can give you, seriously. Go and take pictures. Now, when you take pictures and something doesn't work, then you start asking questions. And this is how you learn. But forget about, if you get the best equipment and go once in a year somewhere and thinking I will get the best image, this is not how it works, okay? Now, the lenses. Lenses, again, is pretty much anything. I would say there are several classes of lenses, like there's a fisheye lens, which gives you 360 degrees, almost field of view. There are wide angle lenses, normal tail lenses, super lenses. So pretty much anything works. My only suggestion would be just to get something like a fast lens, which gives like second number here, gives the speed of the lens. The lower the number, the faster the lens, and the shorter the exposure you need to take proper pictures of the sky. So something, let's say 1.8 or 2.8, these are the best numbers probably for this lens. So what this number defines? It defines essentially your exposure time. So of course you want to spend as less time as possible getting a nice picture, and the lower this number, the faster you will get your picture. And let's do the tripod. So then the tripod, what is essentially you need for this type of photography, good tripod, any tripod, anything, like, doesn't matter, don't look at the brand, you don't have to buy this Gitzo tripod for like $1,000, it doesn't really matter. As long as the tripod is stable enough that it keeps your camera fixed reliably, it's fine, okay? So you should be good. And of course the camera remote control, because remember most of the times our exposure times will be pretty long. Start from with 10 seconds, maybe 5 seconds, 30 seconds. So remote control is essential, so you really need it to, because most of the cameras actually even these days, they're not really designed to take exposures longer than 30 seconds. 30 seconds is the typical range. So if you want to take an exposure longer than 30 seconds, you definitely need the camera remote control. And also the second function of the remote control, it allows you to reduce the vibrations. When you push the button on the camera, at the same time your camera shakes a little bit, yeah? So you really want to avoid the shake, because when you shake, the image will be blurred by the movement of the camera. So in this case, I suggest try the remote control. It will help you mostly to overcome this problem. And the tracker. So what is tracker? I mentioned before that when you take exposure time longer than certain, like a 10-20 seconds with a wide angle lens, let's say 14 or 15 millimeter. So at some point, when your exposure is long enough, you will start to see rotation of the sky. Well, technically it's our planet which rotates, but when we look at our image, we will see stars are moving on your frame. So in order to keep your stars pinpoint sharp, you definitely want your camera to be following the rotation of the Earth with the opposite side. So this is why there is a class of devices which are called tracker. Essentially it's like a small equatorial mount, so which means you set up the camera on this mount, click the button on the mount, and it will be rotating your camera following the stars. And this is the idea how we take long exposures, and in this case you will get pinpoint stars on your images. Like this is an example of the tracker. It's extremely portable. In this case it's Vixen Polari, this Japanese tracker. It's very compact, it's like 300 grams only, size of like a small box. So here you put the ball head, adjust touch your camera, and it will allow you to do exposures for like a couple of minutes. Maybe it depends on your focal length. Now the simplest type of photography in this case is probably would be the star trails, which are still spectacular enough, and it's relatively easy to do. So what are the star trails? So in this case, you set up your camera on the tripod, and you take a series of exposures, like in this case few hundred exposures with a single exposure time equal to like a 10 to 30 seconds, and then using the post-processing technique like in Photoshop, you combine all the images, you stack all the images, and this is what you get. You get, the trails of stars across the sky, and in this case it's pretty remarkable. You see reflections. This is the dish of the CES telescope, radio telescope in La Silla, when you can see reflections. Actually, this is pretty much real, because this is a sub-millimeter antenna. When you stand next to this antenna at the observatory, you see the stars reflecting there, so the reflectivity is very high. So it's pretty impressive just to be there at night and just witnessing how all the stars are rotating. And for that, as I said, this is the simplest way to do photography, because you don't need any tracker. You just need your camera, you just need the tripod, and remote control to take a few hundreds of images on the course of like a few hours. And this is the results you get. Easy and simple. This is another example of the star trails. And the star trails, actually surprisingly, you can do here. You can do it even here in the city. So you don't need like a super good sky. Like this image was taken during the full moon. You see the star tracks are colorless. Foreground is well illuminated. Actually, here this mountain, it was taken at my observatory where I work. This mountain is where this GMT, the Giant Magellan Telescope, will be installed. So it's just a few kilometers away from the Magellan telescopes, and that's the ocean. And here is another example now, almost the same place, but now this image is taken during the dark time, and now you see all the colors of stars. So you see it's pretty easy again. Here there was exposure probably about 8 hours in total. So I left my camera taking images throughout all night. And then I combined all images in one single one, and you see there's a foreground and the stars. The biggest problem in this type of photography, probably, if you're in location which is dark enough, you won't get much of the foreground. Everything will be kind of black, so you will most probably get like a silhouette, but you will not get much of the details of the foreground. And this is the case where we can do so-called blend, as I mentioned before, blend type of imaging. So we take lots of images in the sky, but at the same time we also take one image of the foreground before or after the series of images, and then we combine them in Photoshop using post-processing techniques, and this is how it was done. So these are actually a combination of the sky image, which I combined all those star trails into one image of the star trail. And you see, it was totally dark here. There was no details because there was so little signal in the foreground. And then I took another image here with a longer exposure than the sky. It was probably a minute exposure time. And then just using the masking technique in Photoshop, I just combined two images and create, as we discussed before, this blend image. And this is the way how we create these images. So the Milky Way, when it comes to the Milky Way, again, the southern hemisphere probably would be one of the best places to come because the Milky Way is really impressive. Like on the left side is the image taken at Las Campanas Observatory, when you see the Southern Cross culminating and the Alpha and Beta Centauri. The Eta Carina Nebula, beautiful. See a little bit of color of the air glow here. So the Milky Way goes really up in the sky, passing through the zenith. And it's a better example here on the right side. What you see here, the Milky Way, the galactic center is this galactic center region. The region is called bulge of the galaxy. So this area, this image was taken at Isoparanal Observatory, and this is the actual entrance into the residence of the hotel. So imagine this is almost like a real view. When you just walk in during the night at Isoparanal Observatory, all up the way, and you see the most brightest part of the Milky Way just above your head. So this is pretty much real view. The only difference is, I try to make this image as real as possible. The only difference is the colors. Because remember, at night, our eyes, we don't really see the color of the Milky Way at all. We see colors only on the bright stars of the planes, but we don't really see the colors of the Milky Way. But otherwise, it's pretty real image. So if you're lucky enough to be at Paranal at night for some reason, then you will be able to see this picture. It's really impressive view, just why you should go to the southern hemisphere. On the other hand, there is a time of the year, like for example now, when the Milky Way sets completely, and then what you see is just what we call extragalactic window. We see just absolutely empty piece of the sky, just with the Magellanic Clouds, and you see the Milky Way just goes around the horizon. It's completely set. What you see here is the zodiacal light. I will explain later what is this. But yeah, there is a time of the year when we don't see any Milky Way for a few hours, and it feels surreal because you stay like in completely empty sky, there are very few stars, just Magellanic Clouds, just pretty impressive. So in this case, this is an example of panoramic imaging. So this is not one single image. So this image is a complicated stitch of about 15 other images taken with the same lens, where I rotated the camera on the sky, and then I stitched all these images in the special software designed for panoramic imaging, and this is how I made this image. So it's a bit complicated image, and it's not a single shot in this case. Here's another example, the summer Milky Way. Well, in this case, summer Milky Way means summer like in your sense, because for us this was like May, or April. So you see this is an example again, the advantage of the southern hemisphere, because the southern hemisphere at some point when the Milky Way with the galactic center, which is here, just passes through the zenith. This is amazing, and you see this is the moment when you see the geometry of the Milky Way. It's like the galaxy you can see from the edge. So this is the northern galactic pole, this is the southern galactic pole here. And from this picture, you see this is the north of the galaxy, this is the south of the galaxy. And from this picture, you can actually deduce, answer the question, where do we live in our galaxy? We know we live close to the galactic plane, but from which side? Are we above the galaxy or we are below the galactic plane? Where do we live in the galaxy? We are, or in the galactic plane?
In the plane.
in the plane, but if you just go a little bit above or a little bit below. From this picture, it's easy to see. This is the north, this is the south. Let's say this is above, this is below. You see, we live below because you see, we see more bright light coming from here, so which means more dust is here. We see a little bit more bright spot because we are located just below. We can see the bright part from here. This one is extincted by the dust, so we live a little bit below. Well, in space there is no like above and below, but we are saying if we define this as north, this is south, we are close to the southern pole of the galaxy in this case. Now, and this is the VLT. The image was taken at the Isoparanal Observatory with all these VLTs observed now. Yeah. Now, there is another question which is absolutely, I mean, probably the second most asked question after the equipment. Because first question when people ask you when they look at the images, like what kind of equipment did you use, what kind of exposure time. Now, what is the real color of the night sky? Because when you see tons of images around the internet, you see the sky is blue, red, pink, whatever you can imagine is there. So is there like a measure of the real color of the night? What is the proper color of the real night sky? It's a very good question because, and there's not like a single answer to this. Now, this is the image which I took again at Isoparanal Observatory. You see the sky color here is completely neutral, like a grayish black, with some, kind of red tint here, and it's totally natural because this red color comes from the extinction of the light close to the horizon. Is because of the dust. We have some absorption here. But here the sky is pretty much neutral. You see, it's black. And when people say like, oh, the color is black of the night sky, it's not really true because it's black because we just don't see it deep enough. We don't really see, our eye is not designed to look at the darkness. For us, anything at night is black. But if you take a sensitive camera point on the sky, so you will start getting some colors only because our camera is much more sensitive to the light than our eye. And when we start looking at the camera images, in many cases, the color is not black anymore. Like this is an image I took at the Isolasi Observatory. You see, this is color, and this is properly calibrated color, which is kind of, I took a great deal trying to do the color balance. And you see in some part of the sky is still neutral, but on the other, look at this green glow coming from the horizon up there. So the color is not black, it's not gray, it's green, and it's real. So what is this? There is no light pollution. This is observatory is located like 100 kilometers away from any nearby city. And the color is there. You look at the screen, the color is there. Now, this is an image taken from the Isoparanal Observatory. I tried to make it now, it's taken with the fisheye, that's why you see there is a funny projection here. The fisheye lens, it just does some distortion of the image, but it doesn't matter in this case. So I tried to reproduce the image which is very close to what my eye saw when I just walked outside of the VLT control room to those small telescopes and just looked at the sky, and suddenly I saw this kind of bands of, some kind of clouds. Of course, my eyes are not sensitive to color. I couldn't see what is this. But I definitely saw something which is really strange in the sky, and I couldn't explain because for me that was really difficult. So now I pointed the camera and I took an image, and this is what I got. So suddenly the sky turned out to be completely, it's not even colorless anymore. There was a huge bands of the red color coming from, in this case, from the southeast part of the sky. Huge band. So here you see a little bit of light stuff. It's light pollution coming from the nearby mine, like 200 kilometers mine. But the sky was almost in flames, flaming in red color. So what is this? Is it like real or not? I did a great deal of image processing here. I tried to do the color balance, but it never worked. So this color is real. So that's what is air glow. So what is air glow? Air glow is a technical term which describes the phenomenon which happens in the upper part of the atmosphere. So in other words, what we saw on the previous image was totally real. So it's not something which we introduced during the post-processing, but this is a real effect. Here's another image. Now it's taken at Las Campanas Observatory, and again, it was one of the nights I was trying to take a panoramic image of the full sky over the observatory. This is the 1 meter telescope here. You see the yellow light. This is the light coming from the light pollution from the nearby village, town. But otherwise, you see this light is coming from the regions which are located in the mountains. This is the Andes Mountains just right there. So there is no light pollution whatsoever. I mean, but you see huge red bands across all over the sky again. And those are dynamic, the way of moving across the sky. Again, this is not something which you could explain by the artificial light pollution. And here's another image from Paranal Observatory. So Paranal is one of the best places in the Earth for observing night sky. You see suddenly a bit yellowish light pollution, but at the same time, huge bands of orangish red glow over the observatory. And here the green color as well. So what is this? Las Campanas Observatory. Again, this is a recent image obtained earlier this year. Again, you see not just the glow, but look at the intensity of the glow. You see, this is the galactic center here region. This is the brightest part of the Milky Way, so it's close to the horizon, but at some point we actually lose even the image of the Milky Way because it's just sinking in these huge intense lines across the whole sky. The Milky Way here, you see, is almost undistinguishable now from the foreground emission of the yellow color. So what is air glow? So the cause of all those gradients and waves of the sky is air glow. Air glow is a phenomenon, as I said, which happens in the upper part of the atmosphere, and there are several layers in the atmosphere which are responsible for the air glow. So essentially, air glow is the result of interaction of the solar UV radiation with the upper parts of the atmosphere where different molecules and atoms are located. So during the daytime, when the solar UV radiation hits the atmosphere, it excites atoms and the molecules, and then slowly during several hours, this energy is being released by those molecules, and during the release of the energy, we see the transition which corresponds to a certain amount of light emitted by those molecules. And there are several molecules and the atoms in the upper atmosphere, such as OH, it's so-called hydroxyl, the O, the oxygen, the sodium. All those ones participate in the formation of air glow. And depending on the sort of the species, the color will be different. The color of air glow then changes from the deep red up to the bright green. So this is why sometimes you will see very different color, and the variation of color sometimes can be really interesting. Now, what many people, when they look at this image, they may say, "Oh, this is the aurora." So many of you know this phenomenon which is called Aurora Borealis. This beautiful gradients of the sky, flames in the sky, which typically people see in the northern countries, like in Canada, Norway, Iceland, or if you go like New Zealand, you will see really beautiful splashes of sky like this, of color in the sky. Typically the color is green. But I'm talking about air glow now, and air glow has a little bit different physics. The aurora happens only around the poles of our planet, so you will never see aurora here in Hong Kong, never, because it always it's a result of interaction of the charged particles, which follows the magnetic lines of the magnetic pole in Earth and hits our planet from along the magnetic lines only, which just closed itself just around the pole, South Pole or the Northern Pole, while air glow can be observed everywhere on the planet, including here in Hong Kong. For example, if you just drive outside the city, somewhere which the sky is sufficiently dark, and you take a picture of the night sky, so the air glow is pretty much uniform across all the sky with some kind of variations. You will see it later. So in this case, air glow can be observed from anywhere on the planet. So you don't need to travel to Chile or somewhere else to see air glow, so you can see it here in Hong Kong. Just make sure the sky is dark enough and your camera is good enough to capture this phenomenon. Here's another example of air glow, how intense can it be. This is the panoramic, again, it's a panoramic image, it's a panorama taken from the Las Campanas Observatory. This is the telescopes where I work on, this Magellan telescopes. And you see there's the arc of the Milky Way, and it's one of the nights. It was absolutely intense air glow with such incredible structured way distributed over the sky, the ripples here, and the air glow was different colors. It was starting from yellow and up to the green. So you see in the same time we were seeing different air glows coming from different altitudes. Another extreme example of air glow was observed by Isoclinic Observatory when we went there like 4 years ago. We saw the air glow was so intense, again, it's so red color, so that actually what you see here, you see those black stripes? Actually those black stripes, the clear sky. It's just a clear sky, everything else is just air glow. So those are pieces of sky, and this is how you see your color processing is kind of accurate, because this is pretty neutral sky. You know, it's like grayish, blackish, but everything else is red. There was a huge amount of air glow all over the sky. It was so difficult to, and this was actually kind of a pity for us, because in this case I was at the observatory. We were trying to take pictures for European Southern Observatory, that and the National Geographic, they were using those pictures in, for the work of the observatory, just publicize the work of the observatory. And when we took these pictures, it was a disaster for us. We were supposed to take pictures of the beautiful sky over the Paranal Observatory. Instead, we got some kind of horrible sky with air glow, because it's interesting to see as a scientist this thing, but if you show these images to the general audience, they will say, what is this? Many people, when they look at this, they say it's light pollution. It's not. So that's why for us it was kind of a disaster mission that we failed. Now, this is the difference in air glow. You see, sometimes air glow can have really funny shapes. Again, you see what here, just a complete uniform gradient, and suddenly you see some funny shapes inside. Again, this funny shape inside is the real sky, and everything else is just air glow. You see, the air glow can be red or can be green, like it here is in the image from Las Campanas. You see lots of structure. So it's pretty interesting phenomenon which you can always see on the images, and most of the people don't even know what is this. They're just guessing. Again, this is two extreme examples. You see different cameras here, Nikon and Canon, and you see all variations in the colors of air glow. And this is the best way to see how air glow is changing across the sky, because it's almost like a 240 degrees field of view. See, air glow is not constant. There are pieces of the sky where there is no air glow, and some piece of the sky where the air glow is pretty strong. But it's beautiful. So if you're into night sky photography, so air glow is one of the most interesting objects to take picture, because it just adds additional dimension to the images and really give you a nice feeling. So here an example of the lunar eclipse. So when you take image of the night sky, and I really try to promote the idea of taking a panoramic images, because in this case you might get a really big scale of the phenomenon which is happening. For example, during one of the nights a few years ago, we had a lunar eclipse in my observatory here, and during the eclipse, the sky, of course, suddenly became really dark. So during the full moon, of course, you will never see the Milky Way in the way like this. So, but during the eclipse, you suddenly start to see the Milky Way. You can see the really nice panoramas. This is the artificial, of course, light. There's some nearby towns or some lights, and also some air glow as well to see this. So panoramic imaging gives you really nice opportunity to take images like this, like big scale variation across the sky. So I would here try to explain a little bit of physics of air glow, because the idea of when you start taking pictures of the night sky, I always tell to people, just it's not just enough to take a picture, just try to understand what you're taking. You know, each image represents something physical which is happening in this universe. You know, it's happening in the atmosphere. So why air glow is not uniform, but sometimes, as we saw before, there are lots of ripples sometimes, and they're moving across the sky. So what's the physics? The physics is, like in case of Chile, we have the predominant wind which is coming from the Pacific Ocean. And this wind, it hits, the mountains are pretty high, they're going up to 7,000 meters. So at some point this high-speed wind hits the mountain, and then the wave, the gravity wave, the propagation goes high in the upper atmosphere, and just hits the atmosphere from the bottom. So these gravity waves, which are created by the bump, produce this kind of ripple effect in the air glow. And here an example, this is one of the examples of one of the most extreme air glow, when you see like waves are moving all over the sky. So in the foreground you see that we are sitting above the clouds, the observatory. And this again, it's a panoramic image, it's about 160 degrees taken with the Canon 6D and 14mm lens. And in this case you see beautiful formation of the air glow across the sky. And here I will try to show you that air glow is actually pretty dynamic event. So it's not like a picture frozen in the sky. If you take several images, one after the other, and you combine them in what is called time lapse, you will get a dynamic picture of the air glow, which I will show you here. That's what I did. One of the nights when the air glow was extreme, I decided to just point my camera in the sky, and you see how fast those, see the ball, across the sky. So the phenomenon, it's not static. I mean, the air glow is always changing. So this is why when you take several images across the sky, or even the same piece of sky, you will see how air glow will be changing over the time. You can see some highway here. Okay, here is another example of the same night, of the next night. It's another example how dynamic. You see how active the processes are in the atmosphere? They are moving all the time. They're like waves of air glow moving all the time. This is actually another reason if you're familiar with Astro Photography. Sometimes when you take a picture of some kind of your galaxy, a favorite galaxy, the Milky Way, you see so-called gradients all over the place. And those color gradients on your astrophotographical pictures is exactly due to the air glow. And this is why it's so difficult sometimes to correct your gradient of the color in the images, because air glow is not static, it's dynamic, it's changing from one image to another. Okay, here's another image of the air glow, how it could be. There's the all-sky camera from the observatory. You see now, you see the full sky. And you see how dynamic is it? This is one of the examples of extreme air glow. Like the sky was literally on fire. And you see how intense is this? Sometimes you don't see the Milky Way because of the air glow. And actually this is a big problem for professional observers, because imagine, so now we are losing a lot of light from like a distant galaxies or somewhere because of this air glow, which is it shines on the sky, just blocks. And this is another example how bad could it be. There's a few examples of this air glow. Now, what else can we take a picture of the sky? So I'm trying to explain here several phenomena which you take pictures of the sky and you see something you don't really understand. Another source of confusion when you go at the location extremely remote, like you go to Atacama Desert or you go, I don't know, Taiwan or somewhere, Australia. At some point you might take a picture like without even realizing what is this. Like for example, this is the image which was taken from La Silla Observatory soon after the sunset. And suddenly, the person who took the image, this is my image, but I was taking with another person, and when he pointed the camera on the western part of the sky, which was completely empty, free from the Milky Way, he suddenly saw this cone of light. And he was like, what is this, like a light pollution? Or it's just, it's the sunset? No, the sun was set already. So there is something else in the sky. It just appears there, but we don't know. If you really don't know the astronomy or physics, probably you'll be also confused, like, what is this? It looks beautiful, indeed, but what is this? So this phenomenon is called zodiacal light. So this is another image taken from San Pedro de Atacama, from the Atacama Desert, also after the sunset. The sun was already down there. So the zodiacal light is essentially the scattering of this light coming from the sun on the tiny particle located in the solar system plane. And why it's happening? Remember, when our solar system formed, there was first of all, there was a protoplanetary disk, lots of material rotating around the sun. At some point, all these tiny particles start to collide and coagulate, forming planets. At some point, when there's, due to the gravitational rotation around the sun due to the gravity, all those particles were sticking more and more and more, forming big planets. But at the same time, after the space cleared, we still have a lot of amount of dust in the solar system, which rotates around the sun as our planets, and the plane in the solar system plane, the same plane. So not all dust sticked into the planets. There is lots of leftovers, and those leftovers makes like a cloud of dust in the solar system plane, and the reflections on these dust particles produce so-called zodiacal light. Why it's called zodiacal light? Because it goes along the ecliptic. So the ecliptic is an imaginary line which represents the solar system plane on the sky. This is the plane where the planets move, by the way, on the sky. So this is what we call ecliptic. So the zodiacal light just sees strictly along the ecliptic. So in this case, when you see zodiacal light, you see immediately like a planets will be located somewhere here, 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 maybe along this imaginary line. So all planets won't be found here or there. They always follow the solar system plane. So the planets will be located right here. And here's another example of the zodiacal light in the Milky Way, visible from a parallel observatory. It's a single image from the fisheye lens. It's like a 15mm fisheye lens Canon 6D. And you see zodiacal light, how it goes almost up to the zenith here. So because the sky is so clear in the mountains that you're able to see zodiacal light. Zodiacal light actually is a pretty good indicator of the quality of the night sky. So if you see zodiacal light, this is basically tells you the sky is perfect. You cannot see zodiacal light, like for example here, you will never see this anymore because it's light pollution. But if you go to some site which is located far from the city and you see this cone of light, you can see it either in the morning or in the afternoon just after the sunset. Usually see it only before or after. And this is how you know, yes, the site is good and it's good for astronomy and probably for taking pictures as well. Now, coming back to the same image, the panoramic image, you see the zodiacal light is taken in the morning. You see this is the line of the ecliptic, so the planets will be like just going on the sky along this imaginary line. So this is the zodiacal light, much bigger scale now. See, it's the ecliptic line. Yeah, so zodiacal light in the Milky Way. So here, what we do, I applied another technique. This is the blend images, as they call it. Because actually this is not a blend, it's a panoramic image in this case. But unlike panorama, which you've seen before, it's a horizontal panorama. Here there is another technique which I use, it's called vertical panorama, or some people call it vertorama. So this is like 3 images taken, image number 1, then I move the camera up to get a bit of Milky Way and moved it up again. So I took 3 images, one above another, and then I use the software for panoramic imaging just to stitch those images together to find common points and produce this vertical image. This is the only way to obtain such a large field of view if you don't have a proper lens. And in this case, when you do panorama, the resolution also will be higher. So this is the image also taken in parallel observatory, and this is also image from the parallel observatory. So making panoramas when you just moving your camera several times allows you to produce these images of the Milky Way. It's a very powerful technique to produce high-resolution images as well for printing. And here's another example how you can see the zodiacal light. You see what I was talking about, zodiacal light and the ecliptic line? You see the Venus, Jupiter, and the line of zodiacal light here? Because the inclination changes over the course of the year, orientation changes. So you see the planets, they're not here, they're not there, they're following zodiacal light. Why? Because this is the solar system plane. This is physics just right there. Just you take an image and it's pretty valuable for you just to help you to understand where we are in the solar system. So this is the planets, they follow exactly the zodiacal light, the plane of the solar system. And the sun is just down there, the sun is just below the horizon here. Yeah. The picture was taken just before the sunrise. There is another phenomenon which is absolutely interesting for the nightscape imaging. It's called Gegenschein. So when I said, maybe many of you have never heard about the Gegenschein. So when you go to the extremely dark place, and what I mean extremely, like in this case, this image was taken on the Easter Island in the Southern Pacific. The island belongs to Chile, so it's in the middle of Pacific Ocean, but it's territory of Chile. It's about 5 hours flight over the ocean from Santiago to East Island. So when you go there, you know that you're in the middle of the ocean. There is no artificial light pollution. There is nothing. The sky is extremely dark. So in this case, sometimes even you can see this phenomenon by eye. You might look at the sky and see some faint glow, like extremely faint. Like this is the most faint stuff you could ever possibly see with your eyes on the sky. Sometimes you see it's something like a glowing in the sky. You don't know what is this, but when you take an image, you see there's some structure in there. So this tiny glow has its proper name. It's called Gegenschein. Gegenschein, this is a German word. It was introduced by German first, but it's still used in the naming convention for this phenomenon. Or in English, we call it countershine. Countershine is something like which shines on the opposite side of something. So of what in this case? This is another image which I took from Chile. It's even much more deeper image of the phenomenon which is called Gegenschein. You see, now we see not just some kind of glow, but you see the whole stripe. So why do we see stripe now? When the sky is amazingly dark, super dark, you start to see the stripe. So those two things, it's two pieces of the same phenomenon. So what is the Gegenschein? Gegenschein is, again, the physics is pretty much the same as zodiacal light, but now we are getting the light. Zodiacal light observed just right here, 90 degrees from the sun. But the scattering from the dust, of course, coming from all directions, and the maximum of the scattering as well coming from the opposite side from the sun, in the rotation sun, earth, and anti-solar point. This is where we get another maximum, extremely faint one. So, but this is again, it's a reflection of the sunlight coming from on the particles located in the solar system plane. Again, phenomenon extremely interesting, very difficult to take a picture of, very difficult. Very few people knows what is this, and even if you're lucky enough to take an image of this Gegenschein, most people just ignore it. They don't know what is this. So when you have a camera, another easy way to take a picture of is the meteor showers, of course. Meteor showers, everybody know what is this. It's the particles which are coming in the atmosphere, just burns there and produce this beautiful strike here. If you, during the period of the meteor shower, when the most active, which you point your camera in, which we call the radiant, several hours, during the intense meteor shower, in this case it was a Gemini's meteor shower, the radiant is located in the Gemini's constellation, you will see so many images of the meteors, and then using just a post-processing technique, you combine all those images into a single one, so you will eventually just produce something like this. So in this case, the image was taken, just the image of the foreground. I spent something like only 30 seconds taking one single image of the telescope. Then I took a panoramic image. I stacked like 3 images here of the sky. And then what I've done, I collected few hundreds images of this empty of the sky centered on the radiant a little bit above, and then aligning every streak, then every single image with the final panoramic image. I just aligned all meteors. So in this case, it's kind of something average between blend and the composite image, but scientifically it's correct because every single meteor belongs to this meteor shower, and this is how we get this composite/blend image. Again, it's very easy. You don't need sophisticated tracking or sophisticated processing. You just take one image for the foreground, several images for the sky if you want just to do panoramic image, or just use wide angle lens, and then you just take few hundred images of just area from where meteors are flying in. Then on every single image you pick up one meteor, and then in Photoshop you carefully align those stars and blend your meteor in. It's a very tedious job. You spend usually hours trying to process one single image, but the results kind of interesting. So I like these things.
Extreme.
Wow, the extreme photography. So what do you mean extreme photography? By definition, the night scale photography is kind of extreme because we go at night to locations which are not always safe enough. It's very difficult because first of all it might be dangerous. So can you imagine I realized from my experience, actually taking pictures at night, it's not about like animals, the most dangerous thing at night is people. I'm not afraid of tigers or bears or mountain lions. I've seen them at night, so it was not my problem at all. But I had lots of problems with people at night.
Yeah, people. Yeah.
This is where you want to run and hide. If you see people at night, you want to avoid them at any cost. I mean, because you never know what's going to happen. And many friends of mine had really sometimes really bizarre encounters, starting from crazy guys with rifles and some military approaching you in the middle of nowhere, just asking what you're doing here. I remember experience was really funny. Like in the United States, you know, this country, they have very special gun culture. And then once I was taking pictures, there was some truck just stopped by my camera, and there was a guy came with this big AR-15 rifle, just came to me. And I was like, okay, that's it. So, but it turned out to be a nice guy. We just talked about astronomy. He asked me a few questions what I'm doing, and so at the end it was nice, but it was really uncomfortable. When you see the guy with the armor, you know, just like this huge gun asking, coming to you, it's not the best experience. That's why I feel more comfortable with bear at night than with person. It's difficult. So extreme locations, I will tell about Chile extreme locations, because here we're extreme. What I'm saying, typically when we do imaging in the mountains, we do it negative temperatures. It's like it's very cold. Usually you have to be, actually the cold is more problem becoming for your camera than for you, because for camera might freeze, so you can be really warm enough, but camera is not. So you should take care of your camera. It can be really cold, can be really windy. Sometimes the wind in the mountains go to up to like a 50-60 miles per hour, which is basically blows you away from the ground. So you have to be very, very careful. So in this case, weather conditions, although the sky can be really beautiful like this is the panorama of the lake in the Atacama Desert, in Salar de Atacama, Salt Lake. And the idea was to take an image photographer in front of the Milky Way. And in this case, technically, again, you see what I've done. This is the panoramic image. I took like 3 images here, just image of the lower part of the sky with the photographer, just middle part and the upper part. So again, it was a stitch of 3 images and a very simple processing. There are some clouds just before the sunrise, just to get a nice picture. The high altitude. So in Chile, it's relevant for Chile mostly, because when you go on the high altitude, so the oxygen becomes a real problem. It's not just the temperature, but we also start to lack in oxygen. And this can be just simply dangerous at times. Like in this case, this image was obtained, it's the region which is called Altiplano. It's a high altitude plain in the mountains in the Chilean Andes. So the altitude of this lake is about 4,000 meters here. And the volcanoes here, they're going up to 6,000 meters each. So the idea here was just to capture, you see the orientation of the Big Dipper? Here, it's completely like upside down. So this is what we get in Chile. This is as high as it gets in Chile. So of course we don't see Polaris, but for Chileans, the Big Dipper, this is the way how they see. It's very different. And now we see the reflections of the Big Dipper. So this was my idea, try to get reflections of the Big Dipper in the lake. So when you stay here by the lake, it's difficult because 4,000 meters you're lacking oxygen. It's very cold, and when you lack oxygen, it's also not good for your brain. You kind of start to forget things, and actually this is the real problem. Like you don't really realize until you get to the mountain. So when you're staying, for example, at 4,000 or 5,000 meters, lack of oxygen you don't feel immediately, but you start to forget things. For example, simple example, you just take the cap on your lens cap, you just remove it and put it in your pocket. Then in 5 minutes you want to cover your lens back. And then you start to think where the cup is. You forgot where you put it. Like it's very simple. Or just you forgot sometimes even to open it, because when you take a picture you start to forget it. Yeah, this is real effect. And you become very slow, really slow. You like astronomers who used to work on this altitude. There was a really funny. This site is very close to ALMA Plateau, where this ALMA radio telescope is. And in the early ages of ALMA, when the Europeans put a prototype of the antenna up to this plateau, which is 5,000 meters, they put astronomers in the container next to the telescopes, and the astronomers were spending there a few days and nights observing the sky. And they were noticing the people who stayed on the base camp at much lower altitude, there was a communication between astronomers and the base camp by email at the time. And at some point, it was funny, like in a few days, the astronomers in the base camp started to receive emails from up there, which didn't make any sense. Like people writing something which didn't make any sense, just a set of words. And they just quickly realized, because of the lack of oxygen, people just start to lose the ability to talk properly and to communicate properly. So this is that's myself in my notebook, and this at 5,000 meters with Alma. Here we were trying to take some pictures. It was really cold, and it's one of the examples of the extreme things. I just put my phone, like I said, at 5,000 meters here. It says on the phone. So the idea was to take images of the array of the radio telescopes right here. So again, this is a simple example of how we take the images. We just take a single image for like 30 seconds, and then suddenly during the exposure times, all the antennas start to rotate simultaneously. So when the antennas start to rotate, you got this funny effect of smoothing here on the sky. And you see also the sky is a green color. Again, it's air glow, so this is real. And there's lots of lights coming from the antennas. But in this case, since ALMA, it's a telescope, radio telescope, which works in sub-millimeter. So for them, lights doesn't matter at all. They don't see the light. So they work in the radio. It's very, very different. So for us, the idea was to take images of those antennas under the night sky. And I can tell you another story here, which is directly related to a very popular question among amateur astronomers. How many stars can you see at 5,000 meters? Because when you see in Hong Kong, or whatever, just any land. When I was myself like a young amateur astronomer with my telescope, I was dreaming about Chile. It was my dream to come to Chile. Say, okay, I go to Chile, I climb the mountain, and I will see like millions of stars in the sky. And then my dream came true. I became a professional astronomer. I went to Chile, and then suddenly I went to the 5,000 meters just to see how many stars. And actually it's surprising because when I first went to do imaging with Babak Tafreshi, who is the founder of this one organization. We were 2 photographers at night on Alma's side at 5,000 meters, and we set up our cameras close to the telescope, start to take pictures. And then suddenly we just realized, the sky is really fuzzy, hazy. So we didn't see as many stars as we expected because we just came from Paranal, where the sky was spectacular, this amazing Milky Way. And then we came to the 5,000 meters, and the sky was worse than in Santiago. It was so bad, we couldn't understand why the Milky Way is so bad. So we saw something which we couldn't comprehend, because during the daytime the sky was deep blue because we were high in the mountains, no aerosols, nothing in the air. The sky was extremely clear, so we were surprised why it looks so bad. And this is the image of myself. I was taking with my tripod, my camera on the Polarity tracker, and you see I was taking an image of the Milky Way above the antennas here. You see what is this? Just behind my back, there's some funny device here. And here there's a tube. So due to safety regulations on Alma's side, since it's 5,000 meters, you're obliged to have the oxygen tank behind your back, because and there is a special tube that goes into your nose, and you have to breathe using it's pure oxygen. Because at 5,000 meters, as I said, it's becoming really dangerous because your brain is lacking oxygen, and at some point you're not just forgetting things, you're doing something which might be really dangerous. You're losing sense of danger. For example, there was like a steep cliff here. You're walking on the cliff, which is like few meters down, and you think it's totally okay. You can simply jump down without any fear, because there is no fear at 5,000 meters. So your brain does not realize it can be dangerous for your body. You can die, but you don't think it's okay. You think it's fine. So at this moment, when we were taking pictures of the night sky, normally I think we as a photographers, we felt really good about ourselves. We didn't use oxygens yet. We thought, okay, maybe we're good enough, we're just strong enough. And at some point when we saw the sky was not good enough, we just decided to turn oxygen and to try the idea. Maybe the reason why we didn't see a lot of stars was that our brain doesn't really work well. And indeed, after we switched on oxygen, in a couple of minutes, millions of stars. Millions. So, well, not millions, but a few thousand. So what happens is, this is actually a medical fact that we just learned by ourselves. I didn't really investigate this topic before. But the reason is, when we have a lack of oxygen in our brain, we are not seeing deep enough anymore. So climbing the 5,000 meters and trying to look at the sky without oxygen, doesn't make any good for you. So you won't be able to take advantage of these beautiful conditions here. So medically it was established that the ideal altitude for our human brain, where we still stay sharp and we can comprehend like 100% information coming, it's probably the limit would be about 3,000 meters. Up to 3,000 meters, at 3,000 meters you climb up without oxygen and you will still be able to see like at 100% what your brain is supposed to get. Above 3,000 you start to lose this ability. So at 5,000 you actually losing a lot and you won't see much of the sky. So practically speaking, 3,000 meters is the good, so you don't really have to go up much higher than that. Yeah, that's another panoramic image. And this is the result again of the panoramic image, which take the ideal conditions at the 5,000 meters, the beautiful Milky Way, the zodiacal light here. So again, if you dream about this type of photography, I mean, Chile is the place to go because it has the clearest sky possible. It has amazing transparency, and the configuration of the Milky Way. When you see the Milky Way, just the galactic core just above your head, is just you cannot really describe it. So you really have to see it. So it's really amazing sight. And that's another just view of panoramic image. I'll just do it here. And let's. Yeah, this is how the work of the ALMA. The antennas, you see all antennas, they work simultaneously apart from the one which is just disengaged now. So, but this is the Milky Way. This is a simple sequence of images at like 15 seconds each. It's very simple, but the sky is so good that even in 50 seconds with the Canon 6D, you can get so many details on the sky. Like in this case, as I said, you don't really need sophisticated equipment. You just need to be in the right place probably. Now there is an image. Another thing which is I just mentioned before. It's the safety during the imaging. Like this image I obtained in Sequoia National Park a few months ago in summer when we went to there to take image of Perseids. It's a beautiful waterfall. It's called Grizzly Waterfall. This one. It's really beautiful at night. And this is a real image. Again, it's a blend. It was a separate image taken of the sky, and it was another two images taken of the foreground with much longer exposure times. There is no light painting involved here. So there is one popular technique which is called light painting, when you take image of the sky in the foreground, but since the foreground is so bright, people usually tend to use like a flashlight and just to paint on top. But from my point of view, this type of imaging, it kind of looks pretty much artificial. When you see like a super bright background, it just doesn't really feel the same. So I never do light painting in my photography. Everything is just, I just take long exposure times and then just process it in Photoshop, just extracting details from the very long exposure times. So this is pretty much, I would say, real, which close to what you've seen by eyes, but maybe with the exception of the stones here, which are a little bit brighter than it should be. But here what I want to emphasize that one of the dangers of the nightscape photography, it's you're alone most of the time, and there could be anything like rock people or wild animals sometimes. Like in this case of this part of Sequoia, it's famous with the black bears. So there's lots of black bears around the area. So when you go there, you kind of have to make sure that you're safe. Like this is real. This is the image I took in Yellowstone National Park with the geysers, really beautiful. But this is the place where I encountered the bears of this size. It was like, like my size bear. It was walking just from the other side, just here. And it was at night. It was like complete darkness almost. I was adapted to this, but the bear was just walking to me here. And what do? You stay like here and just with your camera. I don't have, of course, no rifle, no gun. Just although it's in the United States. So luckily the bear was pretty much not interested in me. He just passed by like this, just look at me, just. And because here, see, there is I took image of the path, but there is a much wider area right here. I just stepped to the right just to let him go, and the bear just passed, and I was fine. But it was still uncomfortable because it's a huge bear, like your size. You never know, like because he can just snap you and you're done. Again, so you see, there's a danger. What is I'm trying to say? Safety first. When I wrote here, at night you should be, apart from the camera, you should be aware of what's going on around yourself. You should always constantly check sounds here and there, trying to understand who might be approaching you. Because as I said, people are probably the worst because they can just kill you, snatch your equipment, take it away. Animals are more simple in a way. Most of animals, they're actually afraid of you, even bears. Bears are kind of nice guys because they prefer not to approach people, and if they approach you, if you are not aggressive to them, most, probably 90% of cases, they just let you go. They're not interested in you because they eat other stuff. They just go looking for berries and other things. But it's better to be, of course, aware. And until recently, I was kind of ignorant. I didn't know what to do. And I can give you an advice which I learned the hard way. As I said, I encountered a couple of bears in Yellowstone and this one. And since then, I decided, next time it might be too late. I was just lucky once or twice. But who knows what's going to happen next time. So there is another interesting device which can help you. And I just realized this years ago, if you know what I'm talking about here, the thermal vision. The thermal vision, these things comes from the military. And it's surprising, it's very close to my profession, to what I do. It's a tiny, a pretty much small compact thermal camera. It's infrared, but it's a far infrared. It looks in the range about from 8 to 13 microns, and it looks for heat. It's a thermal vision, and this is how it looks like. Oh. If you look through this camera, it basically records all the signature of heat. So this is why this device you can use in complete darkness, unlike other devices which are called night vision. Usually, you know about devices which are called night vision. There's military guys, go with the Googles, the night vision. So night vision is different. Night vision works on the physics of amplification. So it's basically extremely sensitive photomultipliers which just multiply the light. But they work to a certain extent only, while the thermal imaging, it sends only the temperature. So that's why they're super effective. They can work in total darkness. Night vision doesn't work in total darkness, while thermal vision, it sends the heat. So you can detect animals or people, whatever, from distance of miles away. Like for example, the device which I was showing you, it can see up to 2 kilometers away. You can see the signature of heat. And in this case, when I have this device now, so when I usually go to take pictures, I always first do scan with this thermal imaging around, and I definitely know within a few hundred meters, I know who is where. If I see a person hiding in the bushes somewhere, I see it in total darkness. And I know, okay, there's a guy sitting there, maybe I'll just go another way. Or for example, this time I went to Alberta, to Canada. We were just looking we saw a bear. We were taking pictures not far from the hotel where I stayed. And then suddenly, I just took my thermal vision. I saw the bears for 50 meters from me. It was just sitting and doing something. Of course, I didn't go there. My intention was to go because it was a really nice spot to take a picture of Orion above, the trees. And I was actually trying to go in there, and then I took my thermal vision device, and I saw the bear sitting just doing some stuff. So, okay, no, I'm not going. So it helps a lot because with the flashlight doesn't really allow you to see, first of all, far away. And second disadvantage of flashlight, it just gives you location. Because if there is a rogue guy somewhere here, if you switch on the flashlight, you see, oh, there's somebody there, they go to you. Okay, thermal vision is the best because you're not using flashlight. You can walk in complete darkness and you can see everything which is happening around you. So this is kind of, I discovered this a year ago only. It's amazing technology. As I said, it came from military, but now luckily it's available for anybody. You can buy it pretty much on Amazon, B&H, wherever you want. It's the lifesaver. Seriously, it helps to. So yeah. And also, if you're lucky to be at the observatory, as I said, unfortunately, this is the image from the Lassie Observatory. Many observatories, they restrict presence at night. So you won't be able to get into the observatory and to take these images. We are kind of lucky in a way, like these guys. So we managed to get there because we're astronomers, we can take images like this. But those of you who are seriously interested in imaging and you really would like to visit professional observatories at night, I would still encourage you to contact the observatory. Because many of them, although there's official policy, it's impossible, but since you are not a tourist in a classical sense, you are a dedicated nightscape photographer, you can simply write, it's a real suggestion. And many of my friends, they did it. You contact the observatory and you just present yourself saying, okay, I'm whatever, a guy from Hong Kong. I take pictures like this. You just give your link to your website or your Instagram saying, I'm in Chile, I would like to visit the observatory and may I have a permission? And you'll be surprised, many times it works. So because the observatory is usually how it works when you take images, the observatory will ask you in exchange to share the images with them and they can use those images in their publications. So you can always ask this. Don't be afraid. If you need any help, just let me know. I can help you. Just maybe just write a letter. Again, I'm not an owner of the observatory. I'm not authorizing the visits, but I'm saying that you can do it. Don't be discouraged. If you're really serious about, like for example, going to Chile or going to US to any observatory, just feel free to contact the observatory. And then you'll be like these guys going to the telescopes and you will be able to take those images. So that's my best advice. So that's it. Thank you so much. Do you have any questions? Yeah.
In addition to the millions of stars that you can see at 5,000 level, so and you can also see the Milky Way, especially during the moonless light. So what will be the color of the Milky Way anyway? Because in Hong Kong we see the Milky Way, but it's only pale white, nothing else.
Yeah, I mean, first of all, with your eyes, no color, regardless of the conditions. That's the first thing which is important. I mean, we are talking about the color on the camera images, the camera, because regardless, even if you're in Atacama, 5,000 meters with full of oxygen, our eyes are still not sensitive enough, so you won't be able to see anything on the sky. So for the camera, the color of the Milky Way is defined by the stellar populations which are in the Milky Way. It's going to be, I would say, mix more closer to like a blue beige, something like this. That's the real color. That's pretty much closer to like a beigeish. Like this. It just comes from the stars, from the ages. So it's the distribution from the diagram.
Oh, Yuri, I got a question about your time lapse. Well, in one of the time lapse, we can see the landscape so clearly, so bright. I wonder the value of exposure. Is this something like over 30 seconds?
No, typically time lapse you never really do more than 30 seconds. Because otherwise, the longer the exposure time, then when you try to combine those images in the sequence, any cinematographic sequence is goes like 24 to 30 frames per second. So if you do very long exposure times to try to combine the sequence, your final movie will be extremely short, just a few seconds. So plus many phenomena that are extremely dynamic, like for example air glow. Air glow can change on the time scale of like 30 seconds even. So not even mention aurora or things like this. So that's why you better keep it. And in this case, when you see the foreground is bright enough, it's just because the ground itself in Atacama Desert is pretty dry. So there is no problem of exposing and getting enough amount of details even in 30 seconds or less. So it's sufficient. But it's not always the case. Again, it depends. If you image somewhere like in the forest, like in the Sequoia Park, no, of course not. You won't be able to do the foreground properly.
I would like to know.
Perfect.
The Milky Way can give a shadow of you on the ground.
Sorry, again?
The Milky Way give a shadow, your shadow on the ground. The Milky Way.
Can the Milky Way cast a shadow?
Oh, that's another good question. Yes, it happens. And this is real. When you're in Atacama Desert, one of the things which many people notice that many people think it's like a myth, it doesn't exist, but in Atacama, when galactic center is really high, it's like close to zenith. So in exceptionally clear nights, you can see the shadow of yourself, and the shadow comes from the Milky Way. So it's so bright. It's that bright. Yes. It's real. And this was confirmed by many people, especially surprisingly not by photographers, but visual observers, because I've got lots of friends from different astronomical forums, And there's always a huge discussion, like, can I see the shadow of the Milky Way? And I've seen guys, like super skeptical guys coming to Atacama and just doing visual observations. They saw the shadow, like, I cannot believe it, but I see it. Yeah. It's the case, it's true. But again, for this, you definitely have to go to southern locations, because when the galactic center is pretty, like here, for example, it's not too high. So the angle is pretty steep, so you can't really see it well. So in order to see it, you need to see the galactic center much, much higher. Because first of all, the extinction is less, so the galactic center is much brighter, and the angle is much sharper, so you can definitely see it.
I guess maybe we have time limited. Last 2 questions.
Yui, I saw that you took photo with your Canon 60. Is it a stock Canon or modified?
It's modified Canon, yeah.
So how do you sure that the color of the aircraft?
Yeah, so basically in this case, to do the color balance, you always have in your frame some reference which is called gray color. So area of some object which is neutral. Like for example here, you see the telescope? So we know that the telescope dome is painted in white. So we know it's kind of neutral color. Or there is some area which is gray, not the ground, because the ground in Atacama is red. So you find something which is white or which is gray, and then like in Photoshop you set a gray point. Or it helps if sometimes you get like clouds. Clouds also, make sure the clouds are not illuminated by the light pollution, light sources. So clouds are gray, always gray at night. So you just use the gray color of the clouds as a gray reference point, and this is how you know your color balance is pretty much correct. Probably no. Depends. I mean, not the clouds, but the surfaces, unilluminated surfaces, you still can do it. Yeah, you can do it.
Anyone? Last question.
Okay.
You said that seeing in transparency is very good. Does that mean that most of the year the jet stream is not over?
What's the
Most of the jet stream,
jet stream? Well, there is a jet stream. Of course, there's a jet stream. The thing is, there are different parts of Atacama Desert. It's not always perfect everywhere, and also jet stream properties are changing as well. So sometimes there are certain parts of Atacama where the jet stream is terrible, like there's huge turbulence, and in some of them it's pretty laminate flow. So you have to find a place.
So normally, southern summer is better than winter because typically the jet streams are.
There is no like a relation, as far as we know. There is no like a seasonal variation saying like a seeing in summer better than in winter. No, it's not like that. It's more under given conditions, certain time, certain day. But there's no like a global seasonal variation of the seeing on the sides. So it's pretty much stable.
So we would like to have a big hand for you. Thank you.